Look up at the night sky on a clear evening, far from the city lights, and let your eyes settle on one of those profound patches of darkness between the stars. It looks like nothing, doesn't it? A simple emptiness, a blank canvas in an ocean of light. But what if I told you that within that apparent nothingness lies one of the greatest mysteries of the cosmos, a mystery so vast it challenges everything we think we know about space, time, and existence itself? These are cosmic voids, incomprehensibly large regions of the universe that can stretch hundreds of millions of light years across, yet appear almost entirely devoid of galaxies, stars, or visible matter. In fact, these voids aren't rare anomalies. They make up more than 80% of the volume of the entire observable universe. That's right, most of the cosmos isn't filled with glittering star clusters or swirling galaxies. It's filled with a well with what seems like nothing. But as we're beginning to understand, nothing might be the most interesting something there is. For centuries, humanity has turned its gaze upward, drawn to the light, the constellations, the nebulae, the radiant dance of celestial bodies. We've built telescopes and launched probes to get closer to the brilliance, but in our fascination with the stars, we largely overlooked the darkness between them. It's only in the last few decades that cosmologists have started to truly appreciate that these cosmic voids are not passive absences but active, dynamic players in the evolution of the universe. They are not empty. They are arenas where dark energy flexes its influence, where gravity behaves in unexpected ways, and where the very rules of physics are put to the test. Within these great expanses of seeming nothingness, the fate of the cosmos is quietly, inexorably being shaped. So what are these voids really? Why do they expand faster than the universe itself? Could they be hiding unknown forms of matter, or even clues to other dimensions? And perhaps most intriguingly, how does studying almost nothing help us understand almost everything? In this video, we're going to journey into the heart of these cosmic mysteries, exploring why voids force us to rethink dark energy, the nature of emptiness, and the ultimate destiny of all we see. This isn't just a story about faraway space, it's a story about the fabric of reality itself and our place within it. So come with me as we venture into the great nothing and discover why it isn't nothing at all. To truly grasp the scale we're talking about, picture our own Milky Way galaxy. It's a staggering 100,000 light years across, a number so large it's difficult to even comprehend. Now, imagine a space so vast it could comfortably hold thousands of Milky Ways lined up in a row with room to spare. That is the sheer, breathtaking immensity of a typical cosmic void. These are not small pockets of emptiness. They are the dominant architectural feature of our universe, the grand ballrooms in the cosmic mansion, while the galaxies we usually focus on are merely the furniture clustered in the hallways. The discovery of this true structure was a revolution in cosmology. For a long time, we assumed matter was distributed more or less evenly throughout space. But starting with pioneering surveys in the 1980s, like the Center for Astrophysics Redshift Survey, astronomers began meticulously mapping the universe in 3 dimensions. They weren't just plotting points, they were uncovering a hidden blueprint. Instead of a random scattering, galaxies were arranged in an intricate web-like pattern, a cosmic web of dense filaments and massive clusters intersecting at nodes. And between these brilliant threads of light, enormous, dark, and seemingly empty bubbles, this sponge-like structure forced us to completely abandon the idea of a uniform cosmos and accept a much more complex and dynamic reality. It's crucial to understand what a void is not. It is absolutely not a black hole. A black hole is a point of extreme density, a gravitational monster so powerful that not even light can escape its pull. A void is the exact opposite, a region of profound underdensity. It's also not a perfect vacuum. Even in the deepest, darkest void, you would not find a complete absence of matter. The space is still filled with the sparse, ionized gas that permeates the entire universe, along with a thin sprinkling of dim, isolated galaxies, and we believe a diffuse haze of dark matter. The key difference is one of comparison. The density of matter in a void might be only a tenth of the average density of the universe. So while it's not a perfect nothingness, it is the closest thing to it that the laws of physics allow on such a colossal scale. This very underdensity is what makes voids so incredibly valuable to science. They are cosmic time capsules. Because there is so little matter inside them, the gravitational tug of war that shapes denser regions is vastly reduced. This means voids evolve much more slowly and retain a clearer imprint of the universe's initial conditions. By studying their size, distribution, and shape, cosmologists can perform rigorous tests on our most fundamental theories. They can probe the nature of dark energy, the mysterious force accelerating the universe's expansion, which seems to have a more pronounced effect in these empty regions. They can test the laws of gravity itself on the largest scales, questioning if Einstein's general relativity holds true everywhere or if it needs modification in these extreme environments. And they can trace the invisible scaffolding of dark matter, whose gravitational influence ultimately dictated where these voids would form billions of years ago. So far from being boring, empty deserts, these voids are dynamic laboratories, silent and dark, but echoing with the secrets of the cosmos. But to truly appreciate the significance of these cosmic voids, we have to rewind the clock and understand how we even discovered them in the first place. For most of human history, our view of the cosmos was profoundly flat. We saw the stars as a two-dimensional tapestry pinned to a dark ceiling. The concept that galaxies could be distributed in 3 dimensions with vast, empty chasms between them was simply beyond our grasp. The pivotal moment came not with a single eureka discovery, but with the slow, painstaking work of mapping the universe. This monumental task began in earnest in the late 1970s and early 1980s with projects like the landmark Center for Astrophysics Redshift Survey. This was a Herculean effort for its time. Astronomers, including pioneering figures like Margaret Geller, John Huckra, and the duo you mentioned, Brent Tully and J. Richard Fisher, spent countless nights at telescopes, meticulously collecting the light from thousands of galaxies. They weren't just taking pretty pictures, they were using spectrographs to measure a key property called redshift. You see, as the universe expands, it stretches the wavelength of light traveling through it, shifting it toward the red end of the spectrum. By measuring this redshift, astronomers can calculate a galaxy's velocity away from us, and from that, its distance. For the first time, they could plot galaxies not just by their position on the sky, but by their depth in space. And when they started connecting these dots in 3 dimensions, the shocking truth emerged. The dots weren't scattered randomly. They were arranged in long, winding chains and dense knots, and these structures were separated by enormous, startlingly empty regions, gaps so large and so devoid of points that they defied previous statistical models of the universe. It was like meticulously mapping every town and city on Earth, only to discover that the continents were actually just archipelagos in a planetary ocean that was 90% empty water. These early maps were crude by today's standards, but they were revolutionary. They gave us the first tangible evidence of the cosmic web and introduced us to its most prominent feature, the void. However, these initial surveys were like using a low-resolution camera to map a continent. You could see the general outline of the emptiness, but you couldn't discern its fine details, its true shape, or its intricate boundaries. The real quantum leap in our understanding arrived with the dawn of the digital age and the launch of ambitious, automated sky surveys. The undisputed champion of this endeavor is the Sloan Digital Sky Survey, which began operations in 2000. Imagine going from hand drawing a map of a mountain range to having a high-resolution satellite image that shows every tree, every rock, every contour. That was the transformation Sloan provided. Using a dedicated telescope equipped with a massive digital camera, Sloan didn't study hundreds or thousands of galaxies. It catalogued millions. This flood of data allowed cosmologists to move from simply noting the existence of voids to rigorously defining them, measuring their properties, and understanding their anatomy. Algorithms were developed to essentially connect the dots of galaxies to trace the dense filaments and walls, and in doing so, they automatically outlined the empty cells in the cosmic sponge. We learned that voids aren't simple, spherical bubbles. They are complex, amoeba-like volumes with subtle internal structures and evolving boundaries. The Sloan maps revealed the universe's large-scale structure in such stunning, statistically robust detail that voids went from being curious anomalies to recognized fundamental components of cosmic architecture, every bit as important as the clusters and filaments themselves. This entire historical journey, from the first hints in redshift data to the exquisite three-dimensional atlases we have today, is a powerful testament to the symbiosis between technology and discovery. Each leap in telescope design, each improvement in CCD sensor sensitivity, and each new algorithm for processing unimaginably large datasets gave us a clearer window into the void. We came to understand that these vast empty regions are not random cosmic accidents. Their sizes, their distribution, and their very existence are a direct consequence of the initial conditions of the universe. The tiny quantum fluctuations in density that were imprinted in the first fraction of a second after the Big Bang were amplified over billions of years by gravity. The slightly denser patches pulled in more and more matter, eventually forming galaxies and clusters, while the underdense regions expanded and emptied out, becoming the voids we observe today. By studying the pattern of voids, we are essentially reading a fossil record of the infant universe, a snapshot of its primordial imperfections. This historical perspective shows us that every time we built a better tool to look deeper into space, we were also building a better time machine to peer further back into time, with the great cosmic void serving as our guide. So how do we even begin to study something defined by its absence? It's a bit like trying to map the shape of a hole by only studying the dirt around its edges. Astronomers have developed a brilliant and multifaceted toolkit for this very purpose, turning the immense challenge of studying nothing into a rigorous scientific discipline. The first and most fundamental tool is the Galaxy Redshift Survey. This isn't the work of a single telescope but vast, collaborative projects that methodically scan the sky. Think of the Sloan Digital Sky Survey as a cosmic census taker, meticulously recording the position and distance of millions of galaxies. By plotting these points in three-dimensional space, the empty regions, the voids begin to starkly emerge as the gaps in the data. It's like seeing the outline of a giant bubble in a foam of glitter, but modern surveys like the Dark Energy Survey or the upcoming Euclid space mission take this to another level. They don't just find the voids, they characterize them. Sophisticated algorithms, often based on principles like watershed segmentation, The same technique used to identify river basins on a topographic map are used to precisely define a void's complex boundaries and calculate its volume, effectively allowing us to weigh the nothingness. But knowing where a void is only gets you so far. To truly understand its nature and contents, you need to probe the space within it. This is where techniques like gravitational lensing become absolutely essential. Now, we usually think of lensing in the context of massive galaxy clusters bending light from objects behind them, creating dramatic arcs and rings. But the underdense nature of a void creates its own, much more subtle lensing effect. As light from distant galaxies travels through a void, it passes through a region with less gravitational pull than the surrounding universe. This actually causes the light rays to diverge very slightly, creating a faint demagnification, a weakening of the light. It's an incredibly difficult signal to detect, requiring the statistical analysis of the shapes and brightness of thousands of background galaxies. But by measuring this feeble signature, astronomers can literally map the distribution of all matter, including the invisible dark matter within the void itself. It's a powerful reminder that even emptiness has a gravitational fingerprint. Of course, we can't watch a void evolve over billions of years. To understand their life story, how they form, grow, and interact, we must rely on supercomputer simulations. Projects like the Millennium Simulation or the more recent Illustris TNG are virtual universes born from code. They start with the initial conditions of the early cosmos, feed in all the known laws of physics, gravity, dark energy, hydrodynamics, and then let the simulation run. Watching a time-lapse of one of these simulations is breathtaking. You see the cosmic web slowly materialize, and you witness the voids emerge and expand in real time, clearing out matter as they grow. Scientists can then take these perfect, knowable virtual voids and compare them directly to the messy, observed ones from our surveys. Do the sizes match? Do they have the same shapes and numbers? If they don't, it's a clear sign that our understanding of the underlying physics, perhaps the nature of dark energy or gravity itself, might need a tweak. These digital cosmos act as the ultimate testing ground for our theories. Ultimately, the study of cosmic voids is a masterclass in indirect detection. We use the galaxies to outline the emptiness. We use the bending of light to weigh the unseen matter within that emptiness. And we use silicon-based universes to rewind and fast-forward time. Each tool cross-checks and validates the others, building a coherent picture of these vast and mysterious structures. It's a testament to human ingenuity that we can not only detect these great cosmic nothings but measure them, analyze them, and use them to answer some of the biggest questions we can possibly ask. To truly appreciate the role of voids, we need to visualize the universe not as a homogeneous soup of galaxies, but as a grand, three-dimensional tapestry, the cosmic web. This isn't just a poetic metaphor, it's the most accurate description of the large-scale structure of everything that exists. Picture a colossal sponge, or perhaps a network of soap bubbles stretched across billions of light years. The glowing, dense clusters of galaxies are the intersections, the nodes where multiple strands meet. These nodes are connected by long, twisting filaments of galaxies, gas, and dark matter, forming the web's luminous threads. And the empty spaces inside the bubbles of that foam, those are the cosmic voids. They aren't mere gaps or accidents. They are fundamental structural components. In fact, if you could shrink the entire observable universe down to a manageable size, this spongy, web-like architecture is exactly what you would see. The voids are the negative space that gives form and meaning to the positive structures. Without these vast, empty regions, the brilliant clusters and filaments would have no definition. They would just be a blur. The void is what creates the web. This magnificent structure didn't appear overnight. Its origins are buried in the first fleeting moments after the Big Bang. In that seething, primordial fireball, the universe was almost perfectly uniform, but not quite. Thanks to quantum mechanics, there were tiny, random fluctuations in density, regions that were just a fraction of a percent denser or less dense than their surroundings. These minuscule imperfections are the seeds from which the entire cosmic web grew. Over billions of years, gravity acted like a cosmic amplifier, relentlessly pulling matter toward these slightly denser spots. As more matter gathered, its gravitational pull grew stronger, attracting even more matter in a runaway process that eventually formed galaxies, clusters, and the long filaments connecting them. Conversely, the underdense regions, the seeds of future voids, lost their matter to these gravitational hotspots. They expanded and emptied out, becoming the vast, underpopulated domains we observe today. The entire cosmic web, in all its intricate glory, is simply the grown-up version of those infant universe wrinkles. Within this web, voids are not passive bystanders, they are dynamic players. They dominate the volume of the universe, making up well over half of all space. Their boundaries are particularly fascinating zones, where the emptiness of the void meets the dense walls and filaments of the web. These are sites of constant interaction and interesting physics. Galaxies that live on the outskirts of a void near these boundaries can feel the gravitational tug from the denser regions outside, influencing their motion and evolution. Meanwhile, the void itself, with its incredibly weak gravity, exerts a push. As the universe expands, the low-pressure environment inside a void allows dark energy to dominate more effectively, causing the void's boundaries to expand outward faster than the universe as a whole. This pushes on the surrounding filaments and walls, subtly shaping them. It's a continuous, delicate dance between emptiness and fullness, a gravitational feedback loop on a cosmic scale. This architecture is also far from static. The cosmic web is a living, evolving entity. Voids themselves have a life cycle. Smaller voids often merge together over time, like soap bubbles coalescing, to form even larger, more immense supervoids. Their growth isn't just a simple inflation. It's a complex process that influences the entire web's dynamics. The expansion of voids can actually drive the motion of galaxies, creating vast flows where galaxies stream along filaments toward massive clusters, much like water flowing toward a drain. The relentless push from growing voids helps to continually stretch and evolve the web's structure. So, the next time you look up at a seemingly static night sky, remember that you're looking at a dynamic, evolving sculpture of matter and emptiness, with these great cosmic voids acting as the primary architects, constantly reshaping the universe on the grandest of scales. So here we are, standing at the edge of the first and perhaps most fundamental mystery of the cosmic void, the nature of the emptiness itself. We've given it a name that suggests a total absence, a complete and absolute nothing. But in the universe, it turns out true nothingness might not even exist. The moment we point our most sensitive instruments into the heart of a void, that label begins to fray at the edges. We discover that these regions are not the perfect, sterile vacuums of a physics lab. They are more like the most desolate, sparse deserts imaginable. If the dense galaxy clusters are the teeming tropical rainforests of the cosmos, then the voids are the profound, silent Arctic tundras, harsh, isolated, but far from lifeless. They possess their own unique and subtle ecology of matter and energy. Let's start with what we can actually see. Even the largest voids are not completely devoid of galaxies. They are simply missing the bright, bustling metropolises of stars. Instead, they are home to the cosmic equivalent of isolated hermits or small, rural villages. These are often dwarf galaxies, faint, small, and evolving in near-total isolation, without the gravitational jostling and frequent collisions that their cousins in clusters experience. These void galaxies tend to live quieter, more sedate lives. They often hold onto their primordial gas longer, leading to slower, more sustained rates of star formation. Studying these lonely islands gives us a crucial control group, a way to understand how a galaxy's environment fundamentally shapes its destiny from birth to death. Then there's the gas. Space is never truly empty. It's filled with a thin, ionized plasma known as the intergalactic medium. In the voids, this gas is even more tenuous, but it's there. Vast, diffuse clouds of hydrogen, the universe's most basic building block, drift through these expanses. While they are too faint to see directly in visible light, we can detect them by the way they absorb specific wavelengths of light from even more distant quasars, acting like cosmic fingerprints imprinted on a beam of light that has traveled across the universe. This tells us that the void is not a true vacuum. It's a very, very thin soup, but the visible stuff, the galaxies and the gas, is just the tip of the iceberg. It accounts for only a tiny fraction of what must actually be there. The real bulk of the void, as with the rest of the universe, is made of the invisible dark matter. Now, the concentration of dark matter in a void is far lower than in a galaxy cluster, but it is by no means absent. Imagine a vast, invisible mountain range. The clusters and filaments are the towering peaks, dense with this mysterious substance. The voids are the expansive, flat valleys between them. The terrain is still there, it's just much, much lower. This diffuse haze of dark matter still contributes to the void's gravitational field, creating a subtle but measurable potential that influences the motion of everything around it. It's the underlying geography of nothingness. This leads us to the truly exotic possibilities, the theoretical frontiers. The extreme underdensity of a void might make it the perfect laboratory to detect phenomena that are completely drowned out elsewhere. Some physicists speculate that the unique conditions inside voids could allow for the accumulation or manifestation of exotic particles that we've yet to discover, like actions or certain types of warm dark matter. Furthermore, the vacuum of space itself is not truly empty according to quantum field theory. It's a seething, bubbling foam of virtual particles popping in and out of existence. This quantum foam is everywhere, but its effects are incredibly subtle. Could the vast, quiet expanse of a void amplify these quantum whispers in some detectable way? And then there's dark energy, the force causing the universe's expansion to accelerate. While its effects are global, its influence might be most starkly apparent in the voids. With so little matter to provide a counteracting gravitational pull, dark energy may dominate the dynamics within a void more completely, making these regions the prime places to study its mysterious properties. The void, in its profound emptiness, might be the one place where the background hum of the universe's most fundamental forces finally becomes audible. Now, if the universe as a whole is expanding, you might assume everything in it is stretching apart at the same steady rate, like dots on an inflating balloon. But the cosmos is far more mischievous than that. It turns out that these cosmic voids aren't just passively riding the wave of universal expansion. They are actively sprinting ahead of it, their boundaries pushing outward at a pace that can actually exceed the Hubble flow. This isn't a subtle difference, it's a profound anomaly that points directly to the most mysterious force in all of physics, dark energy. To understand why, we need to think about gravity not as a force of attraction, but as a force of resistance. In the dense urban centers of the universe, the great galaxy cluster's gravity is the ultimate authority. It pulls matter inward, creating a powerful gravitational tug that acts as a brake on the expansion driven by dark energy. It's a constant tug of war, and in these crowded places, gravity puts up a formidable fight. But venture out into the rural emptiness of a void, and that authority vanishes. With so little matter inside, there's almost no gravitational resistance whatsoever. The brakes are off. This allows the repulsive push of dark energy, which is a property of space itself, to operate unopposed. It's like the difference between trying to run through water and running through air. In the dense clusters, expansion is like wading through a gravitational current. In the void, dark energy can simply let loose. This phenomenon, where the underdense regions accelerate away faster than everything else, is formally known as void expansion or void acceleration. It has a fascinating and counterintuitive effect on the galaxies that lie on the outskirts of these emptinesses. Imagine you're standing on the edge of a rapidly growing void. The space between you and the center of the void is stretching faster than the space elsewhere. From your perspective, it feels less like the void is expanding away from you, and more like you are being pushed away from the void. This gravitational repulsion, caused by the lack of pull from the underdense region, actually contributes to the large-scale flow of galaxies. Galaxies are gently shepherded away from the expanding voids and toward the denser filaments and clusters. The voids aren't just empty, they are actively reshaping the cosmic landscape around them, herding matter into the bright nodes of the cosmic web. This bizarre behavior makes voids the perfect natural laboratory for studying dark energy. In most of the universe, dark energy's signal is weak, masked by the much stronger effects of gravity. But in the pristine quiet of a void, its whisper becomes a shout. By meticulously measuring the rate at which voids grow using those intricate computer simulations and comparing them to observations from galaxy surveys, cosmologists can take the temperature of dark energy. They can measure its strength, its consistency, and perhaps even discern whether its properties have changed over the deep history of the cosmos. The accelerated growth of nothingness, therefore, isn't just a curiosity. It's one of our most powerful tools for predicting the ultimate fate of everything. Will the expansion continue forever, leading to a cold, dark, and empty end? Or will dark energy evolve in some unexpected way? The answers are written in the accelerating boundaries of the great cosmic voids, if we can only learn to read them. But to truly grasp the invisible hand shaping these vast expanses, we must turn our attention to the universe's most enigmatic component, dark matter. It's the ghost in the cosmic machine, an entity we cannot see or touch, yet its gravitational influence is the very reason the universe looks the way it does. Without dark matter, the grand cosmic web, with its brilliant filaments and gaping voids, would simply not exist. Its role is absolutely fundamental, acting as the underlying scaffolding upon which all visible structure is hung. In the very earliest moments after the Big Bang, the universe was a nearly smooth soup of particles, both ordinary and dark. But dark matter, being unaffected by the radiation pressure that buffeted ordinary matter, was the first to start clumping together under its own gravity. It began forming vast, invisible halos, gravitational wells that would later act as traps, pulling in clouds of hydrogen gas that eventually collapsed to form the first stars and galaxies. This process seeded the entire cosmic web. The regions that started with a slight overabundance of dark matter became the future dense clusters and filaments, while the regions with a slight deficit were destined to become the great voids. This initial distribution is everything. A cosmic void doesn't begin its life as an empty hole. It starts as a region that was just a little bit emptier than its surroundings in that primordial dark matter distribution. Think of it like a topographic map of the early universe, where the dark matter halos are the mountains and the future voids are the wide, shallow valleys. As gravity works over billions of years, it exaggerates these initial differences in a process cosmologists call gravitational instability. Matter flows from the low-density regions into the high-density regions. The valleys get wider and shallower, while the mountain peaks grow ever taller and sharper. Within the developing void, the few dark matter halos that did exist are too small and too weak to hold onto their matter. The gravitational pull from the massive clusters outside is far stronger, steadily draining material away from the void's center and toward its edges. This process efficiently evacuates the region, leaving behind an ever-growing sphere of profound underdensity. The dark matter is still there, but it's now stretched into an incredibly diffuse, smooth haze, a faint gravitational echo of the structure that never was. What's fascinating is how this distribution differs from the clumpy, chaotic nature of dark matter in clusters. In a dense galaxy cluster, dark matter is thought to form an incredibly complex and lumpy halo, with subhalos within halos, all resulting from a long and violent history of collisions and mergers. But inside a void, the story is one of quiet simplicity. The dark matter has had a much more placid existence, with far fewer gravitational interactions to disturb it. This results in a much smoother, more homogeneous distribution. This smoothness has a direct effect on the motion of the few galaxies that do reside within the void. Without the strong, jerky gravitational tugs from numerous large dark matter clumps, these isolated galaxies tend to drift on much smoother and more predictable orbits. They are gentle travelers in a sea of invisible, smooth energy, rather than participants in a violent gravitational demolition derby. Proving this, of course, is a monumental challenge. How do you map something that is, by definition, invisible? The answer, once again, lies in the subtle art of gravitational lensing. While we typically associate strong lensing with the dramatic arcs around massive clusters, the underdense voids create their own unique, albeit far more feeble, lensing signature. As light from distant galaxies passes through a void, it travels through a region with less gravitational pull than the average density of the universe. This causes the light rays to diverge very slightly instead of converging, creating a minute demagnification effect. It's an incredibly weak signal, impossible to see for a single galaxy. But by statistically analyzing the shapes and brightness of hundreds of thousands of background galaxies seen through a void, astronomers can detect this collective slight weakening. This delicate measurement allows them to essentially weigh the void and create a map of its total mass distribution, revealing the smooth, tenuous cloud of dark matter that permeates the apparent nothingness. It's a stunning achievement, using the absence of gravity to chart the presence of the invisible. This intricate dance between the seen and the unseen, between the emptiness of a void and the pervasive ghost of dark matter that defines its very form, is a cornerstone of modern cosmology. But if the dominant presence of dark matter in voids is a fascinating puzzle, it also opens the door to an even more thrilling possibility. What if the voids aren't just filled with the dark matter we already suspect exists? What if they are hiding something entirely new? The profound emptiness of these regions makes them the universe's ultimate clean rooms. In our dense, messy neighborhood of the Milky Way, any subtle signal from an exotic particle or a rare quantum event is completely drowned out by the background noise of stars, gas, and all the other energetic phenomena of a busy galaxy. It's like trying to hear a whisper in the middle of a roaring rock concert, but step into the void and the concert hall is almost empty. The deafening background noise drops to a barely audible hum. In that pristine silence, the faintest of whispers, the signature of something we've never detected before, might finally become audible. This is why theorists get so excited about cosmic voids. They are the perfect hunting grounds for candidates that lie beyond our standard model of particle physics. Take the hypothetical action, for instance. This is a lightweight particle originally proposed to solve a complex problem in particle physics involving the strong nuclear force. While it has never been directly observed, it's a leading candidate for what cold, dark matter might be made of. In the crowded environment of a galaxy cluster, actions would be incredibly difficult to pick out, but in the diffuse, quiet expanse of a void, their behavior might be different. Some models suggest that the unique conditions could allow actions to congregate or behave in ways that create faint, but detectable, imprints on light or other radiation passing through. It's a long shot, but the void is the one place where that shot is even possible. Similarly, the idea of warm, dark matter, a hypothetical middle ground between fast-moving, hot, and slow-moving, cold varieties, could also be tested here. Warm dark matter would tend to smooth out structure on small scales, potentially leading to voids that are even emptier or have a different size distribution than what our current cold dark matter models predict. By meticulously cataloging the precise emptiness and shapes of thousands of voids, we are indirectly conducting a massive particle physics experiment on a cosmic scale. And it doesn't stop at dark matter. The near-perfect vacuum of a void might be the only place where the true, weird nature of empty space itself becomes apparent. According to quantum mechanics, a perfect vacuum isn't empty at all. It's a seething, bubbling foam of virtual particles, pairs of particles and antiparticles that spontaneously pop into existence for an infinitesimally brief moment before annihilating each other. This quantum jitter is happening everywhere, all the time, but its effects are vanishingly small and impossible to measure directly in our local, matter-filled environment. But in a void where the influence of real matter is at its absolute minimum, could these quantum fluctuations be amplified? Could they, over these immense volumes, produce some collective effect that bends light in a strange way or creates a faint, anomalous energy field that we could, in principle, detect? It's a wildly speculative idea, but it underscores a profound point. By studying the largest examples of nothing we can find, we might be peering into the fundamental fabric of space-time. This potential hasn't been lost on the teams designing our most ambitious experiments. Scientists working with the cosmic microwave background, the afterglow of the Big Bang, pay very close attention to the coldest spots in that ancient light. Some of those cold spots align eerily with the locations of known supervoids, due to a complex energy trade called the integrated Sachs-Wolf effect. But what if some of those cold spots are too cold? What if they can't be perfectly explained by the voids we already know about? That discrepancy could be a hint, a tiny crack in our models where the signature of an unknown form of energy or matter is leaking through. Projects like the Future Square Kilometer Array Radio Telescope are being designed with the explicit goal of mapping the hydrogen gas in and around voids with unprecedented precision, looking for any slight wiggle or warp in the distribution that doesn't fit the standard script. The pursuit of these mysteries transforms the void from a passive absence into an active scientific instrument. We are learning to use these great cosmic holes as lenses to focus our search for the new and the unknown. The very emptiness we once overlooked is now a beacon, guiding us toward a deeper understanding of the particles and forces that compose reality. It's a beautiful paradox. To find what is missing from our models of the universe, we must first learn to truly see the places where it seems like everything is missing. Now, let's shift our focus from the grand, invisible architecture of the cosmos to the intimate lives of its individual inhabitants, the galaxies. Just as a child raised in a bustling city will have a profoundly different life from one raised on a remote, isolated island. A galaxy's environment fundamentally dictates its destiny. And there is no more extreme or revealing environment than the profound isolation of a cosmic void. Here, in these vast deserts of space, galaxies evolve on a path entirely their own, offering us a pristine, almost controlled experiment in how a galaxy grows up when it's left almost completely alone. To appreciate just how different life is for a void galaxy, we need to understand the chaotic reality of a galaxy living in a dense cluster. Imagine a galactic megalopolis like the famous Coma cluster, where thousands of galaxies are packed into a relatively small volume of space. It's a cosmic freeway during rush hour, an environment of constant gravitational harassment. Galaxies frequently swing past each other at incredible speeds, their gravitational fields pulling and distorting each other, triggering massive bursts of new star formation. They sometimes collide in monumental mergers, a violent process that can completely tear apart their elegant spiral structures and forge them into giant, featureless elliptical galaxies. It's a dramatic, fast-paced life, burning brightly but often burning out quickly, using up its raw gas fuel in a series of fiery, explosive events. Now, transport a galaxy from that chaos and place it in the center of a void like the Boötes void. The difference is staggering. It is the ultimate cosmic countryside. The nearest major galaxy could be tens of millions of light years away. This isolation means that for billions of years, a void galaxy might never have a close encounter with another galaxy of significant size. It is spared the gravitational bullying and the catastrophic mergers. Its existence is one of profound quiet and solitude. This peace and quiet has a direct and observable impact on its very structure. Without the gravitational perturbations that constantly stir up and compress gas clouds in cluster galaxies, star formation in a void galaxy proceeds at a much more leisurely, regulated pace. It's not shut off entirely, but it's a slow and steady trickle rather than a series of violent bursts. This leads to a population of stars that is, on average, younger than their cluster counterparts. We see this in their photogenic blue hues, the telltale color of hot, young, massive stars. They are, in a sense, cosmic late bloomers, taking their time to develop. This isolation also means they are incredible hoarders. In a cluster, a galaxy can have its precious reserves of primordial hydrogen gas, the fuel for future stars, stripped away by a process called ram pressure stripping. As the galaxy moves at high speed through the thin but searingly hot gas that permeates the cluster, it acts like a mighty wind, blowing the galaxy's gas out behind it like smoke from a chimney, starving it of the material needed to make new stars. But a void galaxy sails through an ocean of nothing. There is no hot intra-cluster medium to rob it. There are no nearby galaxies to gravitationally steal its gas. Consequently, these isolated galaxies can often hold onto their ancient gaseous fuel reserves for much, much longer. They are cosmic museums, preserving conditions that haven't existed in cluster galaxies for eons. Systematic studies like the dedicated Void Galaxy Survey have meticulously catalogued these differences. They confirm that void galaxies are typically smaller, less massive, and have simpler structures. They are far more likely to retain their beautiful spiral forms, as there's been nothing to disrupt them. Their supermassive black holes, which lurk at their centers, are also different. In a dense cluster, a black hole is constantly being fed by gas funneled in during interactions, flaring up as a brilliant active galactic nucleus. In a void, the central black hole is often starved and quiescent, a sleeping giant that rarely wakes. Even the feedback from the deaths of stars' supernova explosions works differently. In a crowded cluster, a supernova's shockwave might collide with gas from a neighboring galaxy, creating a complex chain reaction. In the void, that shockwave expands out into nothingness, dissipating without affecting any other objects, a silent firework in an empty sky. By studying these galactic hermits, astronomers aren't just learning about one type of galaxy. They are deciphering the most basic, fundamental recipe for how a galaxy evolves when left to its own devices, free from external influence. It allows us to isolate the variables. The void provides the control group in the great experiment of galactic evolution. Every void galaxy is a story of what happens when a universe of potential is given near infinite time and space to unfold on its own terms, telling us a quieter, but no less important, chapter in the epic story of how galaxies live and die. When we first began to map these immense cosmic voids, it was natural to picture them as perfect spheres, simple, elegant bubbles of emptiness floating in the dark sea of space. This spherical model was a useful starting point, a clean geometric shape that made the complex mathematics of cosmology a little more manageable. But as our telescopes grew more powerful and our simulations more sophisticated, a far more fascinating and intricate reality came into focus. The universe, it turns out, is not a master of simple geometry. It is a sculptor of chaotic, dynamic, and breathtakingly complex forms. The voids are not perfect spheres. They are amoebic, irregular, and often interconnected, resembling the holes in a colossal sponge or the chambers in a honeycomb more than a collection of simple bubbles. This incredible diversity in shape isn't random. It's a direct and lasting imprint of the universe's violent and dramatic history. Each void's form is a fossil record, telling the story of its gravitational battles and alliances with the dense walls and filaments of the cosmic web that surround it. Imagine a new void beginning its life from a small, underdense region in the early universe. As it starts to expand, it doesn't do so in a perfect, symmetrical vacuum. It's immediately pressed and prodded by the gravitational pull of the growing clusters and filaments around it. A massive supercluster on one side will exert a tremendous pull, stretching the void into an elongated, teardrop-like shape. If it's sandwiched between two powerful filaments, it might be squeezed into an irregular, almost rectangular profile. Their boundaries are not sharp, clean lines but fuzzy, evolving zones where the last outposts of matter slowly get pulled away into the surrounding cosmic structures. They are dynamic entities, constantly being reshaped by the gravitational tides of the universe. This complexity is brilliantly revealed in modern galaxy surveys like the Sloan Digital Sky Survey. Astronomers use sophisticated algorithms to automatically identify and map these voids in 3 dimensions. The results are astonishing. Statistical analysis shows that while some voids are nearly spherical, the vast majority exhibit significant ellipticity. They are stretched and squashed. Some even possess intricate internal substructure, like faint tendrils of matter or smaller, secondary voids beginning to merge within them. This isn't just an academic distinction. It has profound consequences for how we use voids as scientific tools. For example, using a void as a standard ruler to measure cosmic distances, a technique based on baryon acoustic oscillations, requires us to know its true size. If we incorrectly assume a highly elliptical void is a sphere, our distance calculations will be wrong, leading to inaccurate measurements of the universe's expansion rate and the properties of dark energy. Computer simulations allow us to watch this morphological dance play out over billions of years. We see voids born, grow, and sometimes collide and merge with their neighbors, creating ever larger supervoids with fantastically complex shapes. We also witness the opposite. A void can be encroached upon and eventually crushed by the aggressive expansion of a neighboring, more powerful void, or squeezed into oblivion by the relentless growth of a massive cluster. They are not static holes, they are living, breathing components of the cosmic web, evolving and interacting in a slow-motion ballet dictated by gravity and dark energy. Recognizing their true, irregular nature is therefore absolutely essential. It moves us from a cartoonish understanding of the universe's large-scale structure to a precise, detailed, and accurate model, one where the very shape of nothingness holds the key to understanding everything. But the story of the cosmic microwave background doesn't end with its creation. That ancient light has been traveling for 13.8 billion years to reach us, and its journey is just as important as its origin. As these primordial photons race across the universe, they don't travel through a perfect vacuum. They pass through the evolving large-scale structure of the cosmos, the very cosmic web of clusters, filaments, and voids that we've been exploring. And when a CMB photon encounters one of these vast, expanding voids, something subtle but profoundly important happens. It experiences an effect with a rather technical name, the integrated Sachs-Wolfe effect. Now let's break that down into something much more intuitive. Think of a photon as a tiny marble rolling across a vast, bumpy landscape. The hills and valleys of this landscape are made of gravity created by the distribution of matter. When the photon rolls into a deep gravitational valley like that of a massive galaxy cluster, it has to roll uphill to get out. This effort costs it energy, and as any physicist will tell you, losing energy for a photon means its wavelength stretches a little bit toward the red end of the spectrum. Conversely, when it rolls out of a valley, it gains energy, blue shifting slightly. Now, in a static universe where these gravitational hills and valleys don't change, the energy a photon loses going in would be perfectly regained coming out. The net effect would be zero, but our universe is not static. It's expanding, and it's dominated by dark energy. This is where the voids become crucial. As a void expands over billions of years, its gravitational valley isn't just moving, it's actually becoming shallower. The gravitational pull of that underdense region is weakening over time. So picture our photon marble approaching a void. It first rolls down a very slight hill into the void, gaining a tiny bit of energy and blue shifting. But by the time it's ready to roll out the other side, the hill it has to climb has become less steep than it was when the photon entered. It doesn't have to expend all the energy it gained to get out. It gets a tiny net energy boost. This collective, integrated gain in energy over the photon's entire journey through the void is the heart of the effect. For a CMB photon, this results in a very slight increase in its temperature. Now, this might sound counterintuitive. We just said this creates a cold spot in the CMB map. Here's the brilliant twist. The effect we just described is for the photon's perspective leaving a void. But remember, the CMB is the afterglow of the Big Bang, and we are observing it from here now. The most significant effect we see is actually the opposite. The most prominent signature comes from photons that passed through a void when its gravitational potential was deeper in the past and is shallower now. The net result of this evolving potential is that these photons appear to us to have lost a minuscule amount of energy compared to photons that traveled through more average regions of space. This energy loss translates to a faint cooling, a cold spot in the map of the microwave sky. This is an incredibly subtle signal. We're talking about temperature differences measured in millionths of a degree. Isolating this specific cold spot caused by a single void from the natural variations in the CMB is like trying to hear a single quiet sigh in a roaring stadium. You can't do it by listening to one person. You need a statistical approach. This is where the power of modern cosmology truly shines. Scientists don't look at one void and one cold spot. They take enormous catalogs containing thousands of identified cosmic voids from galaxy surveys like Sloan Digital Sky Survey. Then, they take the exquisitely detailed, all-sky map of the cosmic microwave background provided by the Planck satellite mission. Using powerful computers, they perform a cross-correlation analysis. They essentially ask a simple question. Statistically, when we know there is a void in a certain direction, is the CMB behind it consistently, ever so slightly colder than the surrounding areas? The answer, after painstaking analysis, is a resounding yes. The correlation is there. This discovery is far more than just a neat trick of light. It is a monumental piece of evidence for the existence of dark energy. The only way those gravitational potentials are evolving and becoming shallower over time in such a way to create this effect is if something is counteracting the natural pull of gravity and accelerating the expansion of the universe. That something is dark energy. By measuring the precise strength of this correlation, how cold the spots are relative to the size and depth of the voids, cosmologists can actually measure the properties of dark energy itself. They can constrain its equation of state, a key parameter that tells us whether dark energy is a constant force, like Einstein's cosmological constant, or something more dynamic and strange that could change over time, potentially leading to a different ultimate fate for the cosmos. This intricate interplay between the oldest light we can see and the largest structures of emptiness we can find provides one of the most independent and compelling tests of our entire cosmological model, turning the great cosmic nothing into a precise instrument for measuring the invisible force that shapes everything. But perhaps the most profound way cosmic voids challenge our understanding is by putting gravity itself on trial. For over a century, Einstein's theory of general relativity has reigned supreme, perfectly predicting the orbit of Mercury, the bending of starlight, and the existence of black holes. It is the bedrock of modern cosmology, but even the most successful theories must be tested in every conceivable environment. And the cosmic void presents a laboratory unlike any other, a place of extreme low density where the rules might just be different. This isn't about overthrowing Einstein. It's about asking if his magnificent description of gravity is the complete story, especially on the largest scales where the mysterious influence of dark energy and dark matter dominate. The core of the challenge lies in the fact that our entire model of the cosmos, from the Big Bang to the cosmic web, is built on a specific recipe. This recipe has two main ingredients: general relativity to describe the force of gravity, and the existence of cold, dark matter to provide the extra mass we know is there. This combination, known as the lambda cold dark matter model, has been spectacularly successful. But it also contains profound mysteries. We don't know what dark matter is, and we have no idea what causes dark energy. This has led some physicists to propose a radical alternative. What if we don't need these invisible components at all? What if, instead, our theory of gravity is simply incomplete? This is the heart of theories like modified Newtonian dynamics or MUND. MUND suggests that on very large scales, or in regions of extremely weak gravitational fields, the force of gravity behaves differently than general relativity predicts. It wouldn't require dark matter. The unusual motions of galaxies would be explained by a tweak to the laws of physics themselves. This is where the pristine emptiness of cosmic voids becomes the ultimate courtroom. In the crowded, high-gravity environment of a galaxy cluster, the effects predicted by MUND and those caused by the presence of dark matter can look very similar. It's difficult to tell the difference between a new law of physics and an invisible substance, but in a void, the gravitational field is incredibly weak, the weakest it can possibly be in the universe. It's a place where any subtle deviation from Einstein's predictions should be magnified, like a single wrong note standing out in a moment of silence. If Mond or another alternative theory is correct, then the motion of the few isolated galaxies within a void, or the way galaxies on the void's outskirts flow, should show a clear and measurable anomaly. Their speeds and trajectories should be ever so slightly different from what the standard model of cosmology forecasts. Scientists are actively hunting for this exact signal. They use those incredibly detailed maps from the Sloan Digital Sky Survey to trace the velocities of thousands of galaxies near voids, constructing what are called velocity fields. They then run sophisticated computer simulations that predict what those velocity fields should look like under the standard rules of general relativity with dark matter. The initial results are tantalizing and controversial. Some studies have suggested that the gravitational pull in and around voids seems a tiny bit weaker than expected. The galaxies aren't moving quite as the standard model says they should. It's as if the void itself is exerting even less gravitational influence than its already minuscule amount of matter would suggest. This could be a flicker of evidence for modified gravity. However, other teams analyze the same data and find it perfectly consistent with general relativity, arguing that the apparent anomalies are due to statistical uncertainties or the complex shapes of the voids themselves. The debate is far from settled, but that's what makes it such a thrilling frontier. Cosmic voids have become the crucial testing ground in a high-stakes battle between two fundamentally different views of the universe. On one side is the established idea that the cosmos is filled with mysterious, invisible stuff that obeys the gravity we know. On the other is the radical proposition that we need to rewrite the laws of gravity themselves. By meticulously measuring the motion of galaxies in the great nothing, we are conducting a direct test of one of physics' most sacred theories. Whether the final verdict upholds Einstein or points toward a new, more revolutionary law, the voids will have provided the key evidence, proving that even in the deepest emptiness, the fundamental rules of the universe are still being written. But these cosmic voids are far from static monuments to emptiness. They are dynamic, living entities with their own stories of birth, growth, and eventual transformation. A life cycle that unfolds over billions of years and mirrors the grandest narrative of the cosmos itself. It all begins not with a bang, but with a whisper, a barely there flaw in the fabric of the newborn universe. In the first fleeting moments after the Big Bang, the cosmos was a seething, ultra-dense soup, but it wasn't perfectly smooth. Thanks to the bizarre rules of quantum mechanics, tiny fluctuations in density were imprinted upon everything regions that were ever so slightly denser or less dense than their surroundings. These quantum ripples are the seeds of all structure. The slightly denser patches would eventually become the great galaxy clusters and filaments, while the slightly emptier patches, those minuscule deficits of matter, were the humble embryos of the future cosmic voids. For a long time in the early, radiation-dominated universe, these seeds remained frozen, unable to grow. But once matter took over, gravity began its slow, relentless work, acting as the ultimate cosmic amplifier. This is where the great evacuation begins. Gravity is a force that pulls matter from regions of low density toward regions of high density. So, as the slightly denser patches began collapsing inward to form the first protogalaxies and clusters, the embryonic voids began to lose what little matter they had. It was a gravitational drainage of epic proportions. Gas streams and dark matter flows were siphoned away from these underdense regions, channeled along the emerging filaments of the cosmic web toward the growing dense nodes. With every particle that left, the gravitational hold of the void weakened further, allowing even more matter to escape more easily. It's a powerful feedback loop. As a void empties, it becomes even better at emptying itself. This process is not a violent explosion, but a gradual, inexorable clearing out. Over hundreds of millions of years, these small underdensities expand, growing from tiny ripples into vast, recognizable spherical volumes of profound emptiness, each one a growing bubble in the cosmic foam. Their adolescence and adulthood are marked by interaction and conflict. A void does not exist in isolation. It is surrounded by other voids and, most importantly, by the dense walls and filaments of the cosmic web. Their growth is not a peaceful, symmetrical expansion. Imagine two expanding soap bubbles beginning to touch. Their boundaries press against each other, and the weaker wall between them will eventually rupture. The two voids then merge, creating a single, larger, and more irregular void. A cosmic consolidation that reshapes the local architecture of the universe. We see evidence of this in the complex, amoeba-like shapes of many large voids. They are often the product of multiple mergers, but this growth can also be stifled. If a void is surrounded by exceptionally powerful and dense structures, like a supercluster, the gravitational pull from that surrounding matter can actually squeeze the void, preventing it from expanding freely or even causing it to slowly collapse back in on itself over eons, its territory reclaimed by the denser web. The ultimate driver of a void's fate, however, is dark energy. This mysterious force, inherent to the fabric of space itself, causes the expansion of the universe to accelerate. And because the gravitational pull inside a void is so weak, dark energy operates here with minimal resistance. This means that as the eons pass, the expansion of voids will begin to outpace the expansion of the universe as a whole. Their boundaries will push outward at an ever-increasing rate, clearing out even more matter and stretching their volumes to mind-boggling proportions. In the far, far future, in a scenario cosmologists call eternal inflation, the accelerated expansion driven by dark energy will cause the cosmic web itself to be torn apart. The brilliant filaments and clusters of galaxies will be isolated from one another, and then the galaxies within those clusters will be ripped apart, and eventually even stars and planets. In this dark, cold, and lonely finale, the voids will be the ultimate victors. They will merge into one another until the entire observable universe becomes one unimaginably vast, ever-expanding void, a true nothingness where the once glorious structures are lost to the horizon forever. Studying this life cycle through sophisticated computer simulations is more than just cosmic history. It is a form of prophecy. By understanding how voids have grown and evolved, we can test our models of dark energy and gravity with incredible precision. The distribution of void sizes and their growth rates act as a cosmic speedometer for the acceleration of the universe. The life and death of these great nothings are inextricably linked to the ultimate fate of everything. Their story, from a quantum whisper to a dominion of emptiness, is a poignant and powerful parallel to the universe's own journey from a hot, dense beginning to a cold, dark, and empty end. In tracing the biography of a void, we are ultimately writing the autobiography of the cosmos. Now, having explored how voids test the known laws of gravity and matter, we venture into perhaps the most speculative and mind-bending frontier of all. Could these vast expanses of nothingness be more than just empty regions within our universe? Could they actually be physical portals or thin spots in the fabric of reality, offering us a fleeting glimpse into other universes or higher dimensions entirely? This idea might sound like the stuff of science fiction, but it emerges from some of the most ambitious theoretical frameworks physicists have ever devised. Frameworks that attempt to answer the deepest questions about the cosmos. One of the most compelling of these is the concept of the brain world, a key part of string theory. In this vision of reality, our entire universe, all three dimensions of space and one of time that we experience, is not all there is. Instead, it is just one three-dimensional brain, short for membrane, floating within a higher dimensional space, often called the bulk. Other universes, with their own unique laws of physics, could be floating on other brains in this bulk, utterly separate and parallel to our own. Under normal circumstances, these parallel brains would be completely invisible and undetectable to us. They would be like ghosts occupying the same space but unable to interact. However, theorists suggest that the force of gravity, unlike all other forces, might be able to leak between these brains, propagating through the higher dimensional bulk. This is where cosmic voids enter the picture as a potential laboratory. If our brain has wrinkles or flaws in it, areas where its fabric is thinner or warped, the influence of a neighboring brain might be more pronounced. The profound underdensity of a cosmic void, with its incredibly weak gravitational field, could be just such a flaw. It's a region where the surface tension of our own universe is at its lowest. In these quiet, empty places, the subtle gravitational tug from a parallel universe on a nearby brain might create a tiny, anomalous effect on the motion of galaxies or the distribution of matter that we could, in principle, detect. It would be an almost impossibly faint signal, like hearing a whisper from another room through a single, thin crack in the wall, but the pristine silence of the void is the one place we might have a chance of hearing it. Beyond the possibility of other universes, voids might also be the best place to find evidence for the extra dimensions themselves that these theories require. If there are more than the three spatial dimensions we know, they are presumably compactified, or curled up on themselves at scales trillions of times smaller than an atom. But some models suggest that in regions of extremely low energy density, the effects of these extra dimensions might not be so tightly constrained. The behavior of gravity could be minutely different. Perhaps the force of attraction would weaken or strengthen in a way that deviates from the inverse square law we expect in a three-dimensional world. Detecting such a deviation in a crowded galaxy cluster is nearly impossible because the gravitational signal is a complex mess of thousands of interactions. But in the clean, simple gravitational field of a void where there are few competing signals, a subtle signature of an extra dimension might rise above the noise. It would be a signature of the universe's true, higher dimensional architecture. Of course, it is crucial to emphasize that these ideas remain highly speculative. There is not a shred of direct, observational evidence for a multiverse or for extra dimensions. These are hypotheses born from mathematical elegance and the desperate need to reconcile gravity with quantum mechanics, not from experimental data. Yet, this is precisely why scientists look to cosmic voids. They represent the ultimate clean slate, the most extreme environment where the rules could be different. When a cosmologist models the distribution of galaxies or the subtle lensing effects in a void and finds a tiny discrepancy that the standard model cannot explain, the first step is to check for errors in the code or the data analysis. But if the anomaly persists, the next thrilling step is to ask if it could be a crack in the model itself, a crack through which we might see a glimpse of a far grander cosmic reality. This transforms the void from a mere absence into a canvas for our most profound questions. It's no longer just about what isn't there, it's about what else could be there, hidden in plain sight, waiting for us to develop the tools and the wisdom to see it. To truly appreciate this deep connection between the silent voids of today and the roaring infancy of the cosmos, we need to journey back to a time before stars, before galaxies, before there was even neutral matter as we know it. For the first several 100,000 years after the Big Bang, the entire universe was a seething, opaque plasma, a scalding soup of protons, electrons, and light. Photons couldn't travel freely. They were constantly bouncing off the electrically charged particles, trapped in a relentless game of cosmic pinball. But this primordial soup wasn't silent. It was ringing like a bell, tiny density fluctuations. Those same quantum seeds that would later grow into the cosmic web acted like a clapper, striking this plasma and sending powerful spherical pressure waves rippling outward through the hot, dense medium. These weren't sound waves as we hear them in air, but they were true acoustic oscillations, waves of compression and rarefaction moving at a significant fraction of the speed of light through the early universe. For nearly 400,000 years, these waves propagated, creating a complex, overlapping interference pattern of peaks and troughs throughout the entire observable cosmos. Then, in a single, transformative moment, everything changed. As the universe expanded, it cooled. Around 380,000 years after the Big Bang, the temperature dropped enough for electrons to combine with protons, forming the first neutral hydrogen atoms in an event called recombination. This was a monumental phase shift. Suddenly, the photons that had been trapped for eons were set free, able to stream across the universe unimpeded. This is the light we detect today as the cosmic microwave background, and it carries a perfect snapshot of that moment, frozen in time. But it also captured the final state of those acoustic waves. The waves stopped in their tracks, their progress frozen by the sudden disappearance of the plasma that had been carrying them. Each wave was caught at a specific radius, the distance it had managed to travel since the beginning. This distance, now known as the sound horizon, became a permanent, standard ruler etched into the fabric of the universe. The map of the CMB shows us the hot and cold spots that correspond to the crests and troughs of these waves at the moment they were frozen. This is where the story of the voids truly begins. The frozen wave pattern didn't just fade away. It provided the blueprint for all future structure. The crests of those waves, the regions of highest density, were the preferential sites where dark matter began to clump, eventually pulling in gas to form the first galaxies and the great clusters and filaments of the cosmic web. But what about the troughs? The regions of lowest density in that ancient wave pattern became the natural centers for the voids. Think of it like a pond after a heavy rain. The ripples on the surface eventually settle, but the debris, the leaves and twigs, will have collected in a pattern that still echoes the original circular waves, often collecting in the calm centers. In the cosmos, the debris is the galaxies, and they are arranged in a vast, three-dimensional shell-like pattern, with a tremendous void at the very center of each of these ancient spherical sound waves. The void is the echo. It is the silent, empty heart of a vibration that began when the universe was less than a second old. This realization gave cosmologists one of the most powerful tools ever conceived, the Baryon acoustic oscillation standard ruler. Because we understand the physics of the early universe so well, we can calculate the exact physical size of that sound horizon. It's about 500 million light-years across. This means that the statistical preference for galaxies to be separated by this specific scale is imprinted on the universe. When we look out into space, we can measure the apparent angular size of this Baryon feature. It's like looking at a ruler held at arm's length. The farther away the ruler is, the smaller it appears. By measuring how small this standard ruler looks at different distances, and thus at different look-back times in cosmic history, we can precisely track how the expansion rate of the universe has changed over billions of years. It provides a direct, clean measurement of the universe's expansion history, a crucial test for our models of dark energy. And this is where voids shift from being a consequence of the Baryon to being an essential tool for measuring it. While the BAO signal is visible in the clustering of galaxies, it can be faint and noisy. The voids, however, provide a pristine and powerful way to sharpen this measurement. Because voids so consistently occupy the centers of these ancient spherical shells, their distribution and sizes are exquisitely sensitive to the BAO scale. By creating massive catalogs of voids and analyzing their spatial distribution, astronomers can detect the BAO signal with incredible precision. It's a case of the absence defining the presence. The pattern of where the nothing is located tells us everything about the sound waves that created it. This void-based approach has become a cornerstone of modern observational cosmology, with projects like the Dark Energy Survey and the upcoming Euclid mission relying heavily on void statistics to tighten their constraints on the nature of dark energy, turning the architecture of emptiness into a precision instrument for measuring the fate of everything. But this relentless acceleration driven by dark energy isn't just a curious fact. It leads us directly to one of the most dramatic and unsettling possibilities for the ultimate end of everything, a cosmic finale known as the Big Rip. In this apocalyptic scenario, dark energy isn't just a constant force. It grows stronger over time, its repulsive power becoming so overwhelmingly dominant that it doesn't just push galaxies apart, it literally tears the fabric of reality itself to shreds. And in this terrifying final act, the cosmic voids we've been exploring aren't just spectators. They are the primary instruments of destruction. Their expansion, which we observe today as a fascinating scientific phenomenon, would become an unstoppable, all-consuming force. As dark energy intensifies, the growth rate of these voids would skyrocket. Their boundaries would push outward at an ever-increasing, exponential pace, not just clearing out the remaining wisps of gas and lonely galaxies, but actively ripping apart the cosmic web that contains them. The filaments and walls that form the universe's large-scale structure would be the first to go, stretched and severed by the encroaching emptiness. The horror of the Big Rip lies in its utter thoroughness and its profoundly intimate violence. It's not enough to simply separate galaxy clusters from one another. As the expansion accelerates beyond all bounds, the gravitational glue holding individual galaxies together would be overcome. First, galaxies would be isolated, then ripped from their own satellite galaxies. The relentless pull of the expanding void would then attack the galaxies themselves, tearing them apart, star from star. But it wouldn't stop there. Next, the gravitational bonds within solar systems would be shattered, planets flung from their stars into the infinite, accelerating darkness. Then, the stars themselves would be torn asunder, and in the final, fleeting moments before the very concept of time loses all meaning, the expansion would target the fundamental building blocks of matter itself. The forces that hold atoms together would be overcome, and every single atom in the universe would be ripped apart, subatomic particles pushed apart by the inflationary force of dark energy, separated by distances that become infinite in an instant. The universe would not just end in cold and darkness, it would end in a state of true, absolute, and irreversible dissolution, where no two particles could ever interact again. It is the most absolute and lonely end conceivable. This isn't just a grim piece of science fiction. It's a serious cosmological model with a specific mathematical parameter, the equation of state of dark energy, often denoted as W. If this value is exactly -1, it corresponds to a constant dark energy force, leading to a more gradual, though still bleak, heat death. But if W is less than -1, meaning dark energy's strength increases over time, the Big Rip becomes a terrifying inevitability. And this is precisely where the study of cosmic voids becomes our most crucial crystal ball. By meticulously measuring the rate at which voids are growing right now, cosmologists can take the temperature of dark energy. They can measure its current strength, and by comparing voids at different distances, and thus from different eras in cosmic history, they can begin to discern if that strength is changing. Are voids today expanding at the exact rate predicted by a constant dark energy model, or is there a slight, yet statistically significant, excess in their growth that hints at a dark energy that is, in fact, getting stronger? The precise mapping of void sizes and their distribution across the universe provides a direct, empirical test for these ultimate fate scenarios. Current observations from projects like the Dark Energy Survey and the Planck satellite are already placing tight constraints on these models. The data so far suggests that while dark energy is most certainly real and driving the acceleration, its equation of state is consistent with being a constant, ever so slightly favoring the more traditional heat-death over the violent Big Rip. But the uncertainty in these measurements still leaves the door open a crack. The behavior of the great cosmic voids, their silent, relentless expansion, is our most sensitive barometer for the storm that may or may not be coming. By continuing to chart their growth with ever more powerful telescopes and surveys, we are not just studying the anatomy of emptiness, we are reading the final chapter of the universe's story before it has been written, searching for clues in the quiet, accelerating drift of nothingness that will one day be all there is. Now, let's turn our attention to the cosmic equivalent of a silent room where even the faintest, most unexpected sound becomes a profound mystery. The profound emptiness of cosmic voids creates the ultimate clean auditory slate for astronomers. In the crowded, noisy neighborhoods of galaxy clusters, the cacophony of stellar births, supernova deaths, and active black holes creates a constant background roar that drowns out subtle or rare signals. But in the void, the background noise drops to a barely perceptible whisper. This makes any anomalous signal that does originate from these regions not just noticeable, but glaringly obvious, like a single, clear note played in an otherwise silent concert hall. It is in these deepest silences that the universe sometimes speaks most clearly, and what it says can be utterly baffling. Consider the case of the mysterious fast radio bursts, or FRBs. These are incredibly powerful, millisecond-long flashes of radio waves that release more energy in a fraction of a second than our sun does in days. While some have been traced back to Magnetar's highly magnetized neutron stars in other galaxies, a significant number have point-of-origin data that seems to emanate from vast, underdense regions of intergalactic space, far from any obvious host galaxy. Finding an FRB source in a void is like hearing a tremendous explosion from the middle of an empty desert with no sight of what could have caused it. The isolated nature of the void environment rules out many of the more common explanations that involve interactions with dense gas clouds or other stars. This forces astrophysicists to consider more exotic possibilities. Could these be the final, dying screams of stars so isolated they have never been seen before? Or perhaps they are the signature of something entirely new, like the catastrophic decay of a primordial black hole or the vibration of a cosmic string, a hypothetical, one-dimensional flaw in the fabric of space-time left over from the Big Bang. The void doesn't create the signal, but its pristine emptiness acts as a filter, stripping away the mundane explanations and leaving only the most intriguing, puzzling possibilities. Beyond FRBs, there are other, more sustained anomalies. There have been reports of faint, unexplained radio halos or diffuse gamma-ray glows that seem to be associated with large void structures. These are not the sharp, pinpoint bursts of an FRB, but a soft, pervasive emission that blankets a vast volume of space. One compelling hypothesis is that this could be the long sought-after signature of dark matter annihilation or decay. Many theories predict that dark matter particles, when they collide with one another, could produce secondary particles like electrons and positrons that then radiate energy as they move through magnetic fields. In a dense environment like a galaxy cluster, this signal would be hopelessly lost in the glare of other energetic processes. But in a void where the visible matter background is almost zero and the magnetic fields are weak and orderly, even a minuscule amount of dark matter particle interaction could produce a detectable, faint glow. A signal like this from a void would be the smoking gun for particle physicists, a direct glimpse into the invisible majority of matter in the cosmos, found precisely where we expected to find almost nothing at all. The pursuit of these unexplained whispers is driving the design of the next generation of astronomical observatories. The Square Kilometre Array, or SKA, is perhaps the most ambitious radio astronomy project ever conceived. Rather than a single dish, it will be a forest of antennas spread across 2 continents, acting as a single telescope with a collecting area of over 1 square kilometre. This colossal instrument will possess the sensitivity to not only detect these faint void signals, but to map them in exquisite detail. It will be able to conduct a deep, systematic survey of the radio sky, specifically targeting known void regions to see if these anomalies are statistical flukes or a pervasive, yet hidden, aspect of the cosmos. The SKA's unparalleled resolution will allow it to pinpoint the location of an FRB within a void to an incredible precision, potentially allowing optical telescopes to swing into action and finally capture a visual image of the source, solving a mystery that has perplexed astronomers for years. Every strange signal from the void is a potential clue, a piece of a puzzle we didn't even know we were supposed to be solving. They remind us that a lack of visible stuff does not equate to a lack of physics. In fact, the opposite is true. The emptiness provides a pristine laboratory where even the weakest forces and the rarest events can leave an unmistakable trace. Whether it's the final death throe of an exotic stellar remnant, the indirect proof of dark matter's nature, or something entirely beyond our current theoretical imagination, these anomalies guarantee that the great cosmic voids will remain at the forefront of discovery, proving that the most profound mysteries are often hidden in the quietest places. Yet even among these titans of emptiness, one stands out as a true superlative, a void so colossal and so profoundly empty that its very existence pushes the boundaries of what our cosmological models deem possible. This is the Boötes Void, named for the constellation in which it resides, a staggering chasm of nothingness that has captivated and confounded astronomers since its discovery in 1981. To truly grasp its scale, imagine a sphere so vast it could comfortably contain 15,000 Milky Way galaxies placed side by side. Now imagine that within this incomprehensible volume, there are almost no galaxies to be found. This is the Great Nothing, a void within the void, and it presents a mystery that is as profound as it is enormous. The story of its discovery is a classic tale of scientific curiosity meeting painstaking observation. Astronomers Robert Kirshner, August Oehmler, Paul Schechter, and Stephen Schechtman were analyzing data from a redshift survey, meticulously mapping the 3-dimensional positions of galaxies. As they charted the region near the Boötes constellation, they encountered a baffling gap. Galaxy after galaxy in their catalogue simply stopped appearing across a vast swath of sky. It wasn't a small pocket of emptiness, it was a yawning chasm that seemed to defy the very notion of a structured universe. Their initial reaction was likely one of disbelief, followed by the meticulous process of verifying that this wasn't an instrumental error or a selection effect. The emptiness was real, they had stumbled upon a cosmic desert of unprecedented proportions, a place where the rules of the cosmic web appeared to have been broken. Its sheer size is what makes the Boötes void such a profound statistical outlier. According to our best models of structure formation, which are built upon those initial quantum fluctuations from the Big Bang, voids of this magnitude are incredibly, almost vanishingly rare. The universe simply shouldn't have had enough time to create such a vast underdensity through the normal process of gravitational evacuation. It's like finding a single, perfectly square mile in the middle of a mountain range that is utterly flat, a feature so out of place it challenges our entire understanding of how landscapes form. Its existence forces cosmologists to ask difficult questions. Did it form from a single, primordial underdensity that was anomalously large, a rare but possible fluke in the early universe? Or could its current form be the result of several smaller voids merging over billions of years, a process of cosmic consolidation that created a supervoid of record-breaking proportions? The answer remains elusive, making Boötes a persistent thorn in the side of overly neat cosmological theories. Within this great emptiness, the few galaxies that do exist are like lone outposts in an infinite desert, and they are fascinating precisely because of their isolation. These aren't the brilliant, bustling spiral galaxies or giant ellipticals we see in clusters. They are often small, irregular, and evolving in near-total solitude. For astronomers, these isolated galaxies are natural laboratories, removed from the gravitational harassment and gas-stripping effects of a crowded cluster environment. They represent a control group for studying galactic evolution. How does a galaxy develop when it never collides with another? How does it process its gas and form stars without any external triggers? Observations suggest that many of these void galaxies are gas-rich and have bluer colors, indicating more recent and ongoing star formation, as if their peaceful existence has allowed them to hold onto their youthful vigor for far longer than their cluster-bound cousins. They are the quiet hermits of the cosmos, living lives of slow, undisturbed evolution. The enigma of the Boötes void ensures it remains a prime target for observation. Every new telescope and survey aims its instruments toward this great emptiness, hoping to glean new insights. The quest is to find even more of its faint, hidden galaxies, to map the tenuous wisps of hydrogen gas that must drift through it, and to precisely measure its true boundaries and shape. With each new observation, we refine our understanding, not just of this one void, but of all voids. Boötes acts as a benchmark, an extreme case study that helps us calibrate our models and our methods. It is a reminder that for all our sophisticated theories and powerful technology, the universe is still capable of producing wonders that stop us in our tracks and force us to reconsider what we think we know. This giant void is more than just an empty space. It is a monument to the scale and mystery of the cosmos, a silent, dark reminder that our exploration has only just begun. But perhaps the most profound way cosmic voids challenge our understanding is by putting gravity itself on trial. For over a century, Einstein's theory of general relativity has reigned supreme, perfectly predicting the orbit of Mercury, the bending of starlight, and the existence of black holes. It is the bedrock of modern cosmology, but even the most successful theories must be tested in every conceivable environment, and the cosmic void presents a laboratory unlike any other, a place of extreme low density where the rules might just be different. This isn't about overthrowing Einstein. It's about asking if his magnificent description of gravity is the complete story, especially on the largest scales where the mysterious influence of dark energy and dark matter dominate. The core of the challenge lies in the fact that our entire model of the cosmos, from the Big Bang to the cosmic web, is built on a specific recipe. This recipe has two main ingredients: general relativity to describe the force of gravity, and the existence of cold, dark matter to provide the extra mass we know is there. This combination, known as the lambda cold dark matter model, has been spectacularly successful, but it also contains profound mysteries. We don't know what dark matter is, and we have no idea what causes dark energy. This has led some physicists to propose a radical alternative. What if we don't need these invisible components at all? What if, instead, our theory of gravity is simply incomplete? This is the heart of theories like modified Newtonian dynamics or MUND. MUND suggests that on very large scales, or in regions of extremely weak gravitational fields, the force of gravity behaves differently than general relativity predicts. It wouldn't require dark matter. The unusual motions of galaxies would be explained by a tweak to the laws of physics themselves. This is where the pristine emptiness of cosmic voids becomes the ultimate courtroom. In the crowded, high-gravity environment of a galaxy cluster, the effects predicted by MUND and those caused by the presence of dark matter can look very similar. It's difficult to tell the difference between a new law of physics and an invisible substance, but in a void, the gravitational field is incredibly weak, the weakest it can possibly be in the universe. It's a place where any subtle deviation from Einstein's predictions should be magnified, like a single wrong note standing out in a moment of silence. If MUND or another alternative theory is correct, then the motion of the few isolated galaxies within a void, or the way galaxies on the void's outskirts flow, should show a clear and measurable anomaly. Their speeds and trajectories should be ever so slightly different from what the standard model of cosmology forecasts. Scientists are actively hunting for this exact signal. They use those incredibly detailed maps from the Sloan Digital Sky Survey to trace the velocities of thousands of galaxies near voids, constructing what are called velocity fields. They then run sophisticated computer simulations that predict what those velocity fields should look like under the standard rules of general relativity with dark matter. The initial results are tantalizing and controversial. Some studies have suggested that the gravitational pull in and around voids seems a tiny bit weaker than expected. The galaxies aren't moving quite as the standard model says they should. It's as if the void itself is exerting even less gravitational influence than its already minuscule amount of matter would suggest. This could be a flicker of evidence for modified gravity. However, other teams analyze the same data and find it perfectly consistent with general relativity, arguing that the apparent anomalies are due to statistical uncertainties or the complex shapes of the voids themselves. The debate is far from settled, but that's what makes it such a thrilling frontier. Cosmic voids have become the crucial testing ground in a high-stakes battle between two fundamentally different views of the universe. On one side is the established idea that the cosmos is filled with mysterious, invisible stuff that obeys the gravity we know. On the other is the radical proposition that we need to rewrite the laws of gravity themselves. By meticulously measuring the motion of galaxies in the great nothing, we are conducting a direct test of one of physics' most sacred theories. Whether the final verdict upholds Einstein or points toward a new, more revolutionary law, the voids will have provided the key evidence, proving that even in the deepest emptiness, the fundamental rules of the universe are still being written. Yet for all the mind-bending physics and the cosmic scale mysteries, perhaps the most profound impact of studying these voids is not on our telescopes or our equations, but on our very perception of reality itself. We've spent this entire journey exploring what voids are, their structure, their physics, their influence. But now we must ask a far more fundamental question. What does it even mean for something to be nothing? This inquiry pushes us beyond the comfortable boundaries of astrophysics and into the realm of philosophy, forcing a confrontation with one of the oldest and most perplexing concepts in human thought. We throw the word nothing around in everyday language with casual ease. An empty room, a blank page, a silent moment. We call these nothing. But the cosmic void reveals this to be a profound illusion, a linguistic shortcut that completely collapses when faced with the true nature of the cosmos. Even in the deepest, most isolated void, the very fabric of space is not inert. According to quantum field theory, what we perceive as a vacuum is a seething, bubbling foam of virtual particles. Pairs of particles and antiparticles spontaneously blink into and out of existence, borrowing energy from the universe for an immeasurably brief instant before annihilating each other and paying the debt back. This isn't some abstract mathematical concept. It's a verified prediction of quantum mechanics with observable effects, like the Casimir force, where two metal plates placed incredibly close together in a vacuum are gently pushed together by the pressure of these quantum fluctuations outside them. So, if even the purest vacuum we can conceptually create is alive with this quantum activity, then the idea of a true, absolute nothingness, a complete and total absence of everything, including space, time, and physical laws, may be a fantasy, a concept that simply cannot exist within our universe. The cosmic void, the very emblem of emptiness, is therefore not empty at all. It is filled with the humming potential of existence itself. This realization shatters our intuitive definitions and forces us to redefine what we mean by nothing. In a relativistic cosmos, emptiness is not an absolute state but a relative one. A void is only empty in comparison to the densely packed filaments of the cosmic web. It is a region of underdensity, not zero density. This shifts nothingness from a noun, a static thing, to an adjective, a description of a relationship. It is defined by what it lacks in comparison to its surroundings. This relational view of emptiness echoes through other fields of thought. In art, the negative space around a sculpture is not merely a blank backdrop. It is an active part of the composition, defining the form and guiding the viewer's eye. In music, the rests and pauses between notes are not simply silence. They create rhythm, tension, and meaning. The void is the universe's ultimate use of negative space. It is not an accident or a forgotten corner. It is an active, dynamic component that gives shape and meaning to the entire cosmic structure. Without the great voids, the brilliant clusters and filaments would have no definition. They would blur into a meaningless, uniform glow. The emptiness is what creates the pattern. It is the silence that makes the music possible. This leads us to an even more unsettling philosophical frontier. If a true nothingness is unattainable, then what is the fundamental substrate of reality? We are used to thinking of the universe as being made of things, particles, fields, galaxies. But the void suggests that the primary reality might be a network of relationships, a cosmic tapestry where presence and absence define each other. The stuff of the universe might be less important than the space between the stuff. Some interpretations of modern physics even suggest that space and time themselves may not be fundamental, but may emerge from something deeper, perhaps a quantum entanglement of information. From this perspective, the void isn't a place where things are missing. It's a place where the underlying code of reality is expressed in its most minimal, stripped-down form. It is the cosmic baseline. Studying it is like a programmer looking at the zeros in binary code. They are just as vital for creating meaning as the ones. The void, therefore, challenges the very primacy of matter. It asks us to consider that existence might be built not on a foundation of solid stuff, but on a framework of relationships and potentials, with emptiness being a necessary and integral part of the whole. Ultimately, the contemplation of the void holds up a mirror to our own existence and our search for meaning. For centuries, humans have looked up at the star-filled night sky and felt a sense of awe, connection, and perhaps comfort in the brilliant light. But to look into the void is to confront a different kind of awe, a sublime and terrifying awe born of scale, emptiness, and our own profound smallness. It can evoke a feeling of cosmic insignificance, a sense that in a universe dominated by vast expanses of nothing, our struggles and triumphs on this pale blue dot are utterly meaningless. Yet this perspective can be flipped. The fact that we are here at all, that conscious beings have evolved on a planet orbiting an average star in a forgotten corner of a galaxy, itself just a speck on the edge of a great void, is perhaps the most astonishing miracle of all. Our ability to even conceive of these voids, to map them, measure them, and ponder their philosophical implications, suggests that meaning is not something out there, inherent in the universe, waiting to be found. Meaning is something we create, a light we shine into the darkness. The void does not give us meaning. It provides the silent, empty canvas upon which we project it. Our science, our art, our love, our curiosity, these are the things that fill the existential void. They are our answer to the silence. In the face of an apparently indifferent cosmos, we choose to create significance. The great cosmic nothing, therefore, becomes the ultimate catalyst for the human something. It is the silent question to which our entire civilization, in all its vibrant, chaotic, and beautiful complexity, is the living, breathing answer. And this remarkable journey of discovery is far from over. In fact, we are standing on the precipice of a new golden age in cosmology, one where our understanding of these cosmic voids is set to be utterly transformed. The next generation of astronomical observatories, both in space and on the ground, are coming online with capabilities so advanced they will make our current maps of the cosmos look like rough sketches. These aren't just incremental upgrades. They are revolutionary instruments designed to probe the deepest mysteries of dark energy, dark matter, and the large-scale structure of the universe, and cosmic voids are at the very top of their target list. The James Webb Space Telescope, for instance, is already turning its golden eye toward the most distant and faint galaxies drifting in the void. Its unparalleled infrared sensitivity allows it to peer through cosmic dust and see the light from galaxies so old and so dim that they were previously invisible to us. By finding and studying these isolated void galaxies at the very edge of observable time, Webb will give us an unprecedented look at how the first structures formed in the most underdense regions of the early universe, testing our models of galaxy evolution in the most extreme environments imaginable. But while Webb offers a powerful, targeted gaze, other missions are designed for a sweeping, all-encompassing census. The Vera C. Rubin Observatory, currently under construction in Chile, will undertake the Legacy Survey of Space and Time, or LSST. This is a project of almost unimaginable scale. Every few nights for a decade, its massive 3.2 billion pixel camera will capture the entire available southern sky, not just once but over and over again. This will create a dynamic, living movie of the cosmos, tracking subtle changes in brightness for billions of objects. For void research, this is a game changer. The LSST will detect and measure the distances to millions of galaxies within and around voids with incredible precision, allowing us to map their three-dimensional structure in finer detail than ever before. This vast statistical power will help us finally answer questions about the true distribution of void shapes and sizes. and by tracking the motions of galaxies on the void boundaries, it will provide exquisitely precise measurements of their growth rate, offering a powerful new test of dark energy's influence. Meanwhile, the European Space Agency's Euclid mission is taking to the skies with a very specific and direct goal: to create the most extensive and accurate three-dimensional map of the universe ever made, specifically to investigate the dark universe. Euclid's Wide Field Telescope is uniquely designed to measure two key phenomena. First, it will perform a galaxy redshift survey of breathtaking scope, charting the positions of over 1 billion galaxies across 10 billion light-years. This will allow it to trace the cosmic web and its voids with a clarity and reach that dwarfs all previous efforts, likely revealing a new population of supervoids we never knew existed. Second, and perhaps even more crucially, Euclid is a master of weak gravitational lensing. It will measure the subtle distortions in the shapes of billions of background galaxies caused by the dark matter that permeates all structures, including the vast, underdense voids. This will let us create detailed mass maps of these empty regions, directly weighing the invisible dark matter within them and testing whether its distribution matches our predictions, or if it holds surprises that could point to new physics. And the revolution doesn't stop with optical light. The upcoming Square Kilometre Array, or SCAR, is a truly monumental project in radio astronomy that will listen to the universe's whispers. This isn't a single dish, but a vast network of thousands of antennas spread across South Africa and Australia, working in concert to form a telescope with a collecting area of over 1 square kilometre. The SCA's sensitivity to neutral hydrogen gas is its superpower. It will be able to detect the faint radio emission from the wispy clouds of hydrogen that drift through the deepest voids, gas that is far too tenuous for any current telescope to see. Mapping this primordial hydrogen will reveal the true gas content of voids and show us how material flows into and out of them over time. It could even detect the faint echoes of cosmic inflation or the signatures of those elusive dark matter particles interacting, turning the great cosmic silence into a symphony of data. Together, this armada of new telescopes will provide a flood of data so rich that it will keep cosmologists busy for decades, data that will be fed into ever more sophisticated supercomputer simulations to refine our models of the cosmos. The future of void astronomy has never looked brighter, promising to transform these great expanses of nothing from cosmic mysteries into our most powerful tools for understanding everything. But this profound isolation also presents a paradox for the possibility of life, a double-edged sword of cosmic proportions. On one hand, the very scarcity that defines a void seems to work against the fundamental recipe for life as we understand it. The building blocks are in desperately short supply. The process of planetary formation relies on a rich reservoir of heavy elements, metals like iron, silicon, and carbon, forged in the hearts of stars and scattered across space by violent supernova explosions. In the dense galactic cities of galaxy clusters, this stardust is abundant, continuously recycled through generations of stars, providing ample material for rocky planets to coalesce. But in the void, the story is one of poverty. The lower overall density of matter means fewer stars have lived and died, leading to a significantly lower metallicity. The galaxies that do form here are often anemic, deficient in the very elements that are the bedrock of terrestrial planets and, arguably, the chemistry of life itself. Finding a planet with a rich composition of heavy elements in a void would be like finding a thriving metropolis in the middle of an untouched primordial desert. The raw materials for construction simply aren't readily available in the local environment. Furthermore, the isolation itself could be a death sentence for the spread and resilience of life, a concept we might call astrobiological island theory. Here on Earth, we have evidence that life can be incredibly tenacious, but its grandest explosions of diversity and complexity often occur when ecosystems are interconnected, allowing for genetic exchange and a rebound from localized catastrophes. In a void galaxy, a civilization or even a biosphere would be the ultimate island, separated from any potential neighbors by millions of light years of utter emptiness. A single planet-wide catastrophe, a supervolcanic eruption, a drastic climate shift, or an asteroid impact could snuff out all life with no possibility of receding from elsewhere. There would be no cosmic cross-pollination, no chance that life from another world might arrive to jumpstart evolution again. It would be a single, fragile candle flame in a vast, dark room, vulnerable to the slightest draft. This extreme isolation suggests that if life does arise in a void, its long-term survival against the relentless odds of cosmic fortune would be a testament to resilience beyond anything we can imagine. Yet, for all these formidable disadvantages, the void environment offers a set of unique and surprising benefits that could foster a very different, and perhaps even more stable, path for intelligent life. The most significant threat in a busy galactic cluster is the constant danger from nearby stellar cataclysms. A supernova explosion within a few dozen light-years of a planet would bathe its atmosphere in lethal radiation, effectively sterilizing the surface and triggering a mass extinction. Gamma-ray bursts, the universe's most powerful explosions, are even more deadly, and their long beams of energy could scour entire galaxies clean of life. In a void, the nearest large star is so far away that these apocalyptic events become negligible concerns. A civilization evolving on a world in a void galaxy would be blessed with a profoundly stable and predictable cosmic neighborhood. They would enjoy an uninterrupted view of the universe, free from the light pollution of countless nearby stars, and they could develop over billions of years without the constant existential threat of a nearby star going boom. This stability could provide the uninterrupted time necessary for intelligence to not only evolve but to flourish and mature over eons, potentially leading to cultures of immense age and wisdom. This line of thinking leads to a fascinating and thrilling speculation. Could the great cosmic voids be the ultimate sanctuary for extremely advanced ancient civilizations? If a society were to achieve mastery over its own star system and overcome the initial resource limitations of its void home, it would find itself in an enviable position. With no nearby threats and millions of years of peace guaranteed by the sheer emptiness surrounding them, such a civilization could focus its energies inward on science, art, and philosophy, or outward on the grandest of engineering projects. Perhaps they would harness the energy of their entire galaxy, constructing Dyson spheres or other megastructures that would be easily detectable across the void but invisible to us in our crowded stellar metropolis. The search for such intelligences, however, presents a unique challenge. Our primary methods for hunting for extraterrestrial intelligence, like SETI, often focus on looking for radio or optical signals deliberately beamed into the cosmos. A void civilization, having never had any neighbors to talk to, might have simply never developed the technology or the inclination to broadcast its existence. They might be the universe's ultimate introverts, content in their solitude, their presence betrayed only by the faint, anomalous energy signatures of their incomprehensibly vast technologies. Beyond the possibility of life on planets orbiting void stars, there is an even more exotic possibility drifting in the darkness itself: rogue planets. These are worlds that have been gravitationally ejected from their birth star systems and now wander the interstellar and even intergalactic void alone. It is estimated that there could be billions of such nomads in our own Milky Way, and the number floating in the space between galaxies in a void is unimaginably large. While most would be frozen, airless rocks, a subset with thick ice shells or active geological heat could maintain vast, subsurface oceans of liquid water, much like Jupiter's moon Europa. Around a stable star, such a world could potentially host life around hydrothermal vents on its ocean floor, completely isolated from the surface and the universe above. In the eternal, sunless night of the void, these rogue planets would be the ultimate sealed ecosystems, life existing in a completely independent pocket, utterly unaware of the concept of a sky or a star. Finding evidence of such life would be nearly impossible, but their potential existence means that even the deepest, starless expanse of a void could be teeming with biological activity, hidden beneath miles of ice on a world that drifts forever between the galaxies, a testament to life's ability to thrive in the most unexpected and isolated of niches. It's a fair question to ask, while we're all dealing with the very real challenges of life on Earth, why should we dedicate immense resources and brilliant minds to studying what is essentially a whole lot of nothing in a faraway corner of the cosmos? The pursuit of understanding cosmic voids might seem like the most abstract ivory tower science imaginable, a luxury with no tangible return on investment. But this perspective misses the profound and very practical truth that the journey to understand the universe, no matter how esoteric the destination may seem, has always been the engine for some of our most transformative earthly advancements. The drive to map the great cosmic nothing is paradoxically filling our lives with something incredibly valuable: progress. Consider the sheer computational challenge of finding a void. You can't just point a telescope at a dark patch of sky and declare it empty. Identifying and characterizing these structures requires sifting through the three-dimensional positions of hundreds of millions of galaxies from surveys like the Sloan Digital Sky Survey. This is a problem of big data on a literally cosmic scale. To solve it, cosmologists have had to pioneer incredibly sophisticated algorithms for pattern recognition, statistical analysis, and three-dimensional mapping. The watershed algorithms used to define the boundaries of voids, for instance, weren't created from scratch. They were adapted from techniques used in machine learning and image processing. These refined tools don't just stay in astronomy departments. They trickle down into the wider world, improving everything from the software that helps doctors identify tumors in MRI scans to the programs that meteorologists use to model complex storm systems and predict the paths of hurricanes. The quest to find the biggest nothing in the universe is directly making us better at finding the smallest, most important somethings right here at home. And it doesn't stop with software. Peering into these incredibly dark, low-signal environments demands the absolute cutting edge in sensor technology. To detect the faint whisper of light from a lone galaxy drifting in a void, or to measure the subtle distortion of its light by the void's weak gravitational lensing effect, engineers must push the limits of sensitivity for digital camera sensors and spectrographs. They have to develop new materials and new methods to minimize noise and maximize the capture of every single precious photon. These advancements in ultra-sensitive, low-light imaging technology have direct parallels in numerous fields. They improve the resolution of satellite imagery for environmental monitoring and agriculture. They lead to better night vision systems for search and rescue operations. They even enhance the sensors in biomedical instruments that can detect a single, rare cancer cell in a blood sample. The hardware designed to see the almost invisible in the depths of space ends up helping us see the previously undetectable in our own world. Perhaps the most profound practical payoff lies in our deepening grasp of fundamental physics. The extreme conditions within cosmic voids provide a unique testing ground for the laws of nature, particularly the nature of gravity and the mysterious properties of dark energy. While it may seem like a distant concern, history has shown us time and again that a revolution in our understanding of fundamental physics rarely stays in the realm of theory for long. When scientists like Faraday and Maxwell unlocked the secrets of electromagnetism in the 19th century, they weren't thinking about a global power grid or wireless communication. They were driven by pure curiosity about the nature of force and field. Yet their impractical research quite literally powered the modern world. Today, by probing the bizarre behavior of gravity in the underdense realms of voids, we are stress-testing our most fundamental theories. Who is to say that a deeper understanding of how dark energy operates won't one day open a door to concepts in energy generation or propulsion that are as unimaginable to us today as a smartphone would have been to a Victorian physicist? The void is the ultimate laboratory for asking the biggest questions, and the answers we find there could ultimately rewrite the book on what is technologically possible. Beyond these tangible technological spin-offs, the study of the void delivers a different kind of dividend, a vital perspective. In our daily lives, consumed by personal ambitions, political divisions, and immediate crises, it's easy to see our human dramas as the center of the universe. But to truly comprehend the scale of the cosmic voids, to internalize that we live in a universe where emptiness is the default state and our galaxy is but a tiny speck on the edge of a vast, expanding bubble of nothingness, is to undergo a profound psychological shift. This isn't a lesson in insignificance, but rather a lesson in humility and connection. It shrinks our ego while simultaneously expanding our sense of wonder. It reminds us that we are all, every single one of us, on this one fragile, life-filled planet, riding through a cosmos of breathtaking scale and mystery together. This cosmic perspective can dissolve artificial barriers and inspire a more unified planetary consciousness, a shift in thinking that may be essential for solving our most pressing global challenges. Ultimately, this endeavor is a powerful testament to the human spirit itself. We are a species compelled to explore, to understand, to push beyond the horizon of the known. The study of cosmic voids is one of the purest expressions of that drive. It may not put food on the table tomorrow, but it nourishes our collective intellect and fuels our innate curiosity. It inspires generations of young people to become scientists, engineers, and mathematicians, ensuring a pipeline of innovation for the future. It teaches us the values of patience, collaboration, and long-term thinking. The economic value of studying nothing is found not in a direct product, but in the process itself, a process that sharpens our minds, expands our capabilities, and reminds us that even when staring into the deepest void, the human capacity for wonder is the one thing that is never, ever empty. Now, you might be thinking that mapping the great cosmic voids is a job reserved for PhDs with access to billion-dollar satellite arrays, and for the most part, that's true. But here's the beautiful secret of modern astronomy. Some of the most important discoveries are now being made by people just like you, sitting at their kitchen tables on their lunch breaks or in their backyards with a modest telescope. The field of void research has been utterly transformed by the power of citizen science, a global movement that proves you don't need a doctorate to contribute to our understanding of the cosmos. This is science democratized, where curiosity and a sharp eye are the only credentials required, and it's opening up the universe in ways professional astronomers could only dream of a generation ago. One of the most impactful gateways into this world is the incredible Galaxy Zoo project. Born from a simple problem, that astronomers had millions of galaxy images from the Sloan Digital Sky Survey, but not enough hours in a lifetime to classify them all. Galaxy Zoo invited the public to help. The premise is elegantly simple. You log on, you complete a brief tutorial, and you're presented with a stunning, real image of a galaxy never before seen by human eyes. Your task is to answer a few basic questions. Is it smooth and round? Does it have spiral arms? Is it simply a star? This act of pattern recognition, something the human brain excels at but computers still struggle with, is invaluable. Every classification helps build a more detailed map of the cosmic web. By identifying where galaxies are not, by flagging those lonely, isolated islands in a sea of darkness, volunteers are effectively tracing the outlines of the voids themselves. The collective effort of hundreds of thousands of volunteers has not only produced research-grade data used in dozens of scientific papers, but has also led to the discovery of entirely new classes of objects, proving that the crowd is far wiser than any single expert. For those who crave a more hands-on experience, the night sky is your laboratory. While you might not have a telescope powerful enough to see the faint, distant galaxies at the heart of the Boötes void, you can absolutely contribute valuable data on brighter void galaxies closer to home. Many of the galaxies that reside on the fringes of smaller, local voids are within reach of amateur equipment. With a dedicated astronomical camera attached to your telescope, you can perform photometry, the precise measurement of a star or galaxy's brightness. By monitoring these void galaxies over weeks, months, and even years, you can help professional astronomers track changes in their luminosity. A sudden, unexpected brightening could indicate a supernova explosion, a cataclysmic event that is crucial for understanding the life cycle of stars in these unique, low-density environments. Your consistent observations create a long-term baseline of data that is simply unavailable anywhere else, turning your backyard into a vital outpost for cosmic census-taking. The data you need to make your own discoveries is no longer locked away in an ivory tower. In a monumental shift toward open science, the vast archives of the world's great sky surveys are now freely available online for anyone to explore. The Sloan Digital Sky Survey Sky Server website, for instance, is a public treasure trove. You can pull up the exact same images and data tables that the pros use, learning to navigate the software and perform your own analyses. With a bit of dedication and the help of online tutorials from universities and fellow enthusiasts, you can learn to measure galaxy redshifts from public spectra or use plotting tools to visualize three-dimensional slices of the universe, hunting for those telltale large-scale gaps that signal a void. There are even online communities and forums where amateur cosmologists share their techniques and findings, offering support and collaboration. This isn't just playing with data, it's genuine research. It's entirely possible that a careful, dedicated amateur, sifting through this public data, could be the first to notice a peculiar alignment of galaxies or an anomalously large empty region that everyone else missed, earning a place in the footnotes of astronomical history. This collective effort does more than just accelerate the pace of discovery. It fundamentally changes the relationship between science and society. Every time a volunteer classifies a galaxy or an amateur astronomer submits a light curve, they are not just providing a data point. They are becoming a stakeholder in humanity's greatest collective project, the quest to understand our universe. This engagement builds scientific literacy and fosters a deep, personal connection to the cosmos that a textbook or a documentary can never provide. It shatters the outdated notion that science is a passive spectacle to be watched from the sidelines. Today, the lines are blurring. The professional astronomer who writes the paper might be relying on data collected by a teacher in Wisconsin, a retired engineer in Chile, and a college student in South Africa, all united by their shared curiosity. This global network of passionate observers is creating a new kind of science, one that is more inclusive, more robust, and far more powerful because it is fueled by the most valuable resource of all, the innate human desire to explore and to understand. Your passion is the engine of progress, proving that the map of the great nothingness will be charted not just by a few elite cartographers, but by a whole world of explorers. Yet this profound emptiness, this cosmic nothingness that we've been exploring through the cold, hard lens of science, is not a concept that lives only in data sets and supercomputer simulations. It has, for as long as humans have looked up at the night sky and felt a shiver of awe, permeated our deepest cultural and creative expressions. The void is not just a physical place in the universe. It is a powerful psychological and philosophical space within us, a canvas upon which we project our greatest fears, our loneliest isolations, and our most boundless hopes. This interplay between the scientific reality of cosmic voids and the human response to the idea of emptiness creates a fascinating feedback loop where discovery fuels art and art, in turn, gives a soul to the equations, making the vast, impersonal cosmos feel intimately relatable. In the visual arts, the concept of the void has been a powerful tool for evoking emotion and scale. Consider the work of a modern artist like Ólafur Eliasson. He doesn't paint pictures of space, he creates physical experiences that mimic the sensation of being enveloped by immensity. One of his most famous installations, called Your Blind Passenger, involves leading people through a long, narrow corridor filled with such a dense, artificially created fog that visibility is reduced to just a few feet. You cannot see the person in front of you or behind you. You lose all sense of direction, distance, and time. It is a visceral, gut-level simulation of being lost in a formless expanse, a direct translation of the emotional weight of a cosmic void into a gallery space. It's not about depicting nothing, it's about making you feel the nothing. This is a far cry from traditional space art filled with brilliant nebulae and galaxies. Eliasson's work, and that of many other contemporary artists, captures the other side of the cosmic coin, the overwhelming, humbling, and strangely beautiful terror of the empty space that makes up the majority of everything. They use absence not as a lack, but as an active material, a presence defined by what is not there. Literature and poetry have long used the void as the ultimate metaphor for existential contemplation. It represents the internal landscape of loneliness, the silent gaps in our understanding of ourselves, and the terrifying freedom of a blank slate. From the bleak, empty spaces in the works of Samuel Beckett, where characters wait in a purgatorial nothingness, to the vast, silent deserts in Frank Herbert's Dune that become a character in themselves, a testing ground for the human spirit, the void is a relentless mirror. In poetry, it's often the space between words, the pauses and the silence that carry the heaviest meaning, much like the empty spaces between stars hold the key to the universe's structure. These creative explorations predated our scientific confirmation of cosmic voids by decades, even centuries. It's as if the human psyche somehow intuited this fundamental truth about the cosmos, that emptiness is a dominant, shaping force, and began processing it through story and verse long before our telescopes could prove it. The artist and the cosmologist are asking the same profound question, simply using different languages to frame it. This cultural conversation finds its most popular and accessible expression in film and video games, where the void is often rendered not as a passive emptiness, but as an active, thrilling, and often terrifying frontier. Think of the heart-stopping tension in Alfonso Cuarón's Gravity, where the serene beauty of Earth orbit transforms in an instant into a lethal abyss. The silence of space in that film is not peaceful, it's deafening and utterly hostile, a void that actively seeks to kill. It taps into a primal human fear of being untethered, lost, and alone. In the world of gaming, titles like No Man's Sky and Elite Dangerous offer players the chance to literally fly into the void, to navigate the unimaginable distances between stars where nothing exists for light years at a time. This gameplay mechanic transforms the abstract concept of a cosmic void into a tangible experience of duration and isolation. The journey itself becomes the story, a test of endurance against the sheer scale of nothingness. And then there are the voids of pure imagination, like the mysterious, reality-bending zones in Andrei Tarkovsky's Stalker, or the ominous, dark space between worlds in the Stranger Things universe. Here, the void is no longer just empty space. It becomes a repository for the unknown, a place where the normal rules of physics and logic break down and anything or nothing might be waiting. It represents the ultimate mystery, the final frontier of both exploration and fear. This beautiful synergy between the scientific and the creative is what truly enriches our understanding. Science provides the factual framework, the mind-boggling scale, the gravitational dynamics, the dark matter distribution. It gives the void its physical properties. But art, in all its forms, gives it meaning. It translates the data into emotion, the facts into feeling. A cosmologist can tell you the exact dimensions of the Boötes void and its statistical significance, but it takes a filmmaker or a novelist to make you feel the profound, soul-shivering loneliness of being adrift within it. One approach appeals to our intellect, the other to our humanity, and neither is complete without the other. The artist is inspired by the latest deep-field image from the James Webb Space Telescope, and in turn, their painting or symphony about that image inspires a young person to become an astronomer. It's a virtuous cycle where the discovery of a colossal nothingness here in the external universe somehow fills us with ever more wonder, creativity, and a desire to connect. The void, in the end, is the greatest possible muse precisely because it is so empty. It offers no answers, only an infinite space for questions, and in that space, the human imagination finds its most powerful and limitless freedom. Of all the mysteries surrounding cosmic voids, perhaps the most pervasive one isn't about the voids themselves, but about the stories we tell about them. Popular science and science fiction have a way of weaving grand, often terrifying, narratives around the concept of emptiness, leading to some deeply ingrained misconceptions that can actually obscure the true wonder of these structures. It's time to clear the air and separate the cosmic fact from the compelling fiction, because understanding what voids are not is just as important as understanding what they are. The most common and understandable myth is right there in the name, the idea that a cosmic void is a perfect, absolute vacuum, a region of true and total nothingness. This notion is so seductive. It taps into a primal fear of emptiness, of the unknown, but the reality is far more nuanced and in many ways more interesting. While the density of matter in a void can be as low as 1/10 the average density of the universe, it is never zero. You would not find a perfect vacuum there. Instead, you would find a sparse collection of the universe's most isolated hermits, faint, dwarf galaxies that have evolved in near total solitude for billions of years. You would find vast, diffuse clouds of ionized hydrogen gas, so thin they are almost undetectable, drifting through the expanse, and you would most certainly find dark matter, not in the dense, clumpy halos we associate with galaxies, but as an incredibly smooth, tenuous haze that still contributes to the void's overall gravitational field. Calling a void empty is like calling a desert waterless. While technically true in comparison to an ocean, it ignores the unique and resilient ecology that exists there. The cacti, the creatures adapted to the aridity, the hidden reservoirs. A void isn't a sterile nullity. It's a cosmic desert with its own subtle, sparse, and fascinating inhabitants. This leads directly to a second, more dramatic misconception, that voids are dangerous, unnatural places where the laws of physics break down. This is a staple of dramatic fiction, the mysterious region of space where engines fail, time stutters, and reality itself becomes unstable. In truth, a cosmic void is one of the most law-abiding places in the universe. The same rules of general relativity that govern the orbit of Earth around the Sun apply perfectly within the void. The same quantum mechanics that describe the behavior of particles in a lab on Earth are in full effect there. If anything, the void is a place where physics is more pure, not less. Without the complex, messy interactions of dense matter, gravitational fields are smoother and more predictable. It's a pristine laboratory, not a haunted house. The only danger of a void is the same danger inherent in any vast, empty wilderness, the peril of isolation and the scarcity of resources. For a hypothetical spaceship, the threat wouldn't be reality breaking down. It would be running out of fuel with no star systems nearby to resupply, a practical problem of distance and logistics, not of fundamental physics failing. Another surprising error is the belief that these voids are rare cosmic anomalies, strange freaks of nature that are few and far between. This couldn't be further from the truth. Our entire perception of the universe is skewed by a profound sampling bias. We live in a universe that is over 80% empty, yet we are obsessed with the less than 20% that is full. We are like a tiny mite living on a single leaf in the Amazon rainforest, convinced that the entire world is a dense green canopy, completely unaware that the vast majority of the planet is actually open ocean and desert. Voids are not the exception, they are the rule. They are the dominant architectural feature of the cosmos, the grand ballrooms in the cosmic mansion. The brilliant galaxies and glittering clusters we focus on are merely the furniture, the decorative accents clustered in the hallways. This shift in perspective is crucial. It means that the empty space is not a background stage upon which galaxies act. It is an active, primary component of the universe's structure. To study the cosmos while ignoring the voids is to try and understand a forest by only looking at the trees, while willfully ignoring the air and the soil between them. Finally, there's the myth of stasis, the idea that these great voids are permanent, unchanging features, simply frozen bubbles in an otherwise dynamic cosmos. Nothing could be more dynamic than a void. They have a life cycle. They are born from tiny underdensities in the early universe. They grow over billions of years by gravitationally evacuating matter toward denser regions. They sometimes merge with neighboring voids like cosmic soap bubbles coalescing, and they are constantly being shaped and molded by the gravitational tides of the surrounding cosmic web. Their boundaries are not sharp, static walls, but fuzzy, evolving zones of interaction. Most importantly, their evolution is directly tied to the most mysterious force in the universe, dark energy. Because the gravitational pull inside a void is so weak, dark energy's repulsive effect operates with minimal resistance, causing voids to expand faster than the universe itself. They are not static, they are the vanguard of the universe's accelerating expansion. They are growing faster than anything else, actively reshaping the large-scale structure of everything. Understanding this dynamism is key to using them as tools to measure dark energy and predict the ultimate fate of the cosmos. Dispelling these myths is about more than just pedantic accuracy. It's about upgrading our sense of wonder. Fear of the unknown is a primitive, simplistic wonder. It's the gasp you make when you jump at a shadow. But the wonder that comes from true understanding is deeper, richer, and infinitely more rewarding. It's the awe you feel when you comprehend the intricate, dynamic dance between presence and absence that has shaped the entire universe. By replacing the fiction of a dead, empty, dangerous void with the reality of a dynamic, subtle, and dominant component of the cosmos, we don't lose a mystery, we trade a cheap thrill for a profound truth. The enlightenment isn't in having all the answers, but in learning to ask better, more insightful questions about the great cosmic nothing that is, we now know, absolutely something. To truly grasp the anatomy of nothingness, we must move beyond awe-inspiring images and venture into the realm of pure mathematics, where the apparent chaos of the cosmic web is distilled into elegant equations and powerful statistical truths. This isn't about dry calculation. It's about uncovering the hidden syntax of the universe, a set of rules written in the language of mathematics that governs the formation, growth, and distribution of these vast, empty regions. The first and most fundamental challenge for cosmologists is a seemingly simple one. How do you even define the edge of something that is defined by its absence? In a three-dimensional map of millions of galaxies, the voids are the gaps, but drawing a line around a gap is a complex geometrical puzzle. This is where sophisticated algorithms come into play, acting as cosmic cartographers for emptiness. One of the most powerful techniques is called Voronoi tessellation. Imagine taking every single galaxy in a survey and assigning to it a unique territory, a cell, that encompasses all the points in space that are closer to that galaxy than to any other. When you do this for the entire dataset, the universe is partitioned into a vast, complex honeycomb of these polyhedral cells. The voids then naturally emerge as the large, contiguous empty spaces at the heart of clusters of these cells. It's a mathematical way of finding the natural, equidistant boundaries between structures. Another method, borrowed from the field of topography, is the watershed algorithm. Here, the density of galaxies is treated like a topographic map, where high-density clusters are the mountain peaks and the low-density voids are the valley basins. The algorithm works like virtual rainfall, tracing the paths that water would take as it flows downhill, away from the dense peaks and into the catchment areas of the voids. The watershed lines, the divides between these catchment basins, become the defined boundaries of the voids themselves. These aren't arbitrary lines on a map. They are mathematically rigorous definitions that allow scientists to consistently measure void properties like volume, shape, and depth across the entire observable universe, turning subjective observation into quantifiable, reproducible science. But finding the voids is only half the battle. The real power of mathematics lies in its ability to predict and explain why the voids are there in the first place, and why they have the specific sizes and distribution that we observe. This brings us to the foundational concept of Gaussian random fields. The theory of cosmic inflation tells us that the minuscule quantum fluctuations that seeded all structure were initially random, but they followed a very specific, predictable pattern of randomness known as a Gaussian distribution. Imagine the surface of a perfectly calm pond suddenly disturbed by a million tiny, random raindrops. The pattern of ripples would be chaotic, but statistically, you could predict the probability of finding a wave of a certain height or a trough of a certain depth. The early universe was like that pond. The Gaussian random field model allows cosmologists to generate millions of virtual universes on a supercomputer, each with a different random sprinkling of these initial density fluctuations. They can then run the laws of physics forward in time in these simulations and watch as the cosmic web forms, crucially, they can count the voids that appear. The model makes a specific statistical prediction. Given the initial conditions of the Big Bang, you should expect a certain number of small voids, a certain number of medium voids, and a vanishingly small number of truly gigantic voids like Boötes. When astronomers then go out and meticulously catalog the voids in the real universe, the match is astonishingly good. The statistics of the observed voids, their size distribution, their shapes, how they cluster with each other align almost perfectly with the predictions from these Gaussian-based models. This agreement is one of the strongest pillars supporting our entire standard model of cosmology. It tells us that the great cosmic voids are not bizarre anomalies. They are the entirely expected, statistical outcome of the universe's random and violent birth, a fossilized echo of its quantum origins. Of course, the universe doesn't stop evolving after that first moment. The simple Gaussian picture provides the initial conditions, but the subsequent growth of voids is a dynamic battle between two titanic forces, the relentless pull of gravity and the mysterious push of dark energy. Describing this battle requires another set of mathematical tools, primarily complex differential equations that track how the density within a void changes over time. The key equation incorporates terms for the expansion of the universe, the gravitational effect of the matter trying to pull the void's boundaries inward, and the repulsive effect of dark energy pushing them outward. Solving these equations analytically with pen and paper is often impossible due to their complexity. This is where numerical simulations become indispensable. Cosmologists input these equations into massive supercomputers, which break down the universe into billions of individual pixels, and then calculate the gravitational and dark energy forces acting on each pixel over billions of years of virtual time. It is through these monumental number-crunching exercises that we discovered the counterintuitive truth that voids expand faster than the universe itself. The simulations showed that the gravitational weakness inside a void allows dark energy to dominate, creating a runaway effect that the equations had always hinted at but that only brute force computation could vividly reveal. This synergy between elegant theory and powerful computation is what allows us to use voids as precision instruments. By tweaking the parameters in these equations, for instance, slightly changing the strength of dark energy or the nature of gravity itself, and running the simulation again, we can see how the resulting population of virtual voids changes. We can then compare these new virtual voids to the real ones we observe. It's a meticulous process of mathematical trial and error, honing in on the exact rules of physics that produce a virtual universe indistinguishable from our own. The mathematics of emptiness, therefore, is far from an abstract exercise. It is the essential toolkit that transforms the void from a curious cosmic feature into a rigorous laboratory, allowing us to weigh the invisible, measure the mysterious, and stress-test the very laws of reality against the clean, dark backdrop of nothingness. But to truly understand the cosmic void, you can't just observe its present state. You have to witness its entire life story unfold over billions of years. This is an obvious impossibility with our limited lifespans, which is why cosmologists have performed one of the most spectacular feats of modern science. They have learned to grow entire universes inside supercomputers. These are not simple animations or artists' impressions. They are rigorous mathematical models known as cosmological simulations, and they are our ultimate time machines for unraveling the birth, life, and death of the great cosmic nothing. Projects with names like Illustris, Achu, and the Millennium Simulation are the digital laboratories where the deepest mysteries of the void are brought to life. The process begins with a set of initial conditions that are, in their own way, a perfect echo of the Big Bang itself. Scientists program in the fundamental parameters of our universe the exact amount of ordinary matter, and dark energy we have observed, along with the specific pattern of those tiny quantum density fluctuations that were imprinted on the cosmos when it was less than a second old. This pristine virtual universe is a near-perfect uniform soup, a blank digital slate waiting for the clock to start ticking. Then, with a command, the simulation begins. The most powerful supercomputers on Earth, humming away in vast climate-controlled halls, start crunching the numbers. They divide this virtual cosmos into billions or even trillions of individual cells and then apply the known laws of physics to each one. The force of gravity is calculated between all particles of dark matter, causing them to slowly clump together. The complex hydrodynamics of gas are modeled, how it heats, cools, collapses, and is shredded by shockwaves from supernova. And crucially, the relentless, repulsive pressure of dark energy is infused into the very fabric of the simulated space itself, driving an accelerated expansion. The computer doesn't just fast-forward through time. It painstakingly calculates every single gravitational interaction, every fluid dynamic pressure, for every cell, for every moment across 13.8 billion years of cosmic evolution. What emerges from this monumental number-crunching exercise is nothing short of breathtaking. You can watch a time lapse of a simulation like Illustris TNG and see it happen. The faint, Gaussian randomness of the initial conditions slowly amplifies. Tiny dark matter overdensities become halos which attract gas, which forms the first stars and galaxies. And simultaneously, the underdensities begin to expand, clearing out, emptying, merging, and growing into vast, intricate voids. The entire cosmic web, with the void as its primary architectural feature, materializes before your eyes not as a static picture, but as a dynamic, evolving entity. The true power of these simulations lies in their ability to act as a controlled laboratory for testing our wildest ideas. A cosmologist can ask a simple, what-if question that would be impossible to test in the real universe. What if dark energy was twice as strong? What if dark matter particles interacted with each other instead of being completely collisionless? What if Einstein's theory of gravity needs a slight tweak on the largest scales? You can adjust these parameters in the simulation, run it again, and watch what happens to the voids. Do they grow faster? Do they become more spherical? Do they merge more frequently? By comparing the detailed properties of the voids in these altered reality simulations to the painstakingly catalogued voids from the Sloan Digital Sky Survey, scientists can perform a rigorous test. If the simulated voids from a modified physics model look more like the real ones than the standard model's voids do, then you might just have a breakthrough on your hands. This is how we stress test our most fundamental theories against the clean, dark canvas of nothingness. Perhaps the most transformative aspect of this technology, however, is its ability to make the inhuman scale of the cosmos tangibly, viscerally real. Raw data from a simulation is just numbers in a grid, but that data can be imported into a virtual reality environment, allowing a researcher or a student to literally step inside the simulation. Strap on a headset and suddenly you are no longer an outside observer. You are an immortal, omnipotent giant, able to fly at impossible speeds through the evolving cosmic web. You can approach a forming void, watching as galaxies are gently pushed toward its ever-expanding boundaries. You can plunge into its heart, turning around to see the entire surrounding universe structured as a brilliant, complex shell of light encircling you, a single point in a sphere of profound darkness. You can witness the slow-motion collision and merger of two voids, a billion-year process compressed into a few awe-inspiring seconds. This immersive experience is more than just a fancy visualization. It is a profound tool for intuition. The abstract concept of large-scale structure is replaced by a direct, embodied understanding of its three-dimensional nature. You don't just learn that voids are connected, you see the tunnels and bridges between them. You don't just read that voids are amoeba-shaped, you can fly around one and appreciate its irregular, complex morphology from every angle. This fusion of cutting-edge computational science with immersive virtual reality technology is democratizing cosmic understanding, turning the most mysterious and empty places in the universe into a space that we can not only study, but truly experience and explore. For centuries, humanity's relationship with the cosmos has been one of pure observation, a distant and passive wonder. But as we stand on the cusp of becoming a truly spacefaring civilization, that relationship is fundamentally changing. We are no longer just stargazers, we are now potential actors on the galactic stage, and this new role comes with a profound and unprecedented set of ethical responsibilities. The vast cosmic voids, those incomprehensible deserts of space, present what might be the ultimate ethical frontier. Their sheer scale and apparent emptiness make them a tantalizing target for future ambitions, but this very emptiness also makes them a unique and fragile part of the cosmic ecosystem. The central, daunting question we must now confront is this: do these voids represent the universe's ultimate resource, waiting for us to exploit, or are they sacred wildernesses, cosmic preserves that deserve to be protected in their pristine state for all time? This isn't a question for some distant future. The principles we establish now will set the precedent for how we interact with the entire universe. Consider the potential for exploitation. The practical allure of these empty regions is undeniable. Their incredible scale offers possibilities that dwarf anything we could conceive within our crowded solar system. One of the most theoretical yet scientifically plausible concepts is the generation of unimaginable energy. The physicist Freeman Dyson once speculated that a sufficiently advanced civilization might construct a vast energy-capturing shell around its star, a Dyson sphere. Now scale that idea up to a void. The complete absence of light-blocking dust and gas, combined with the ability to position solar collectors across billions of miles of empty space without obstruction, could make a void the perfect site for a civilization-scale power grid, harnessing the light of every galaxy on its far distant walls. Furthermore, these voids could become the intergalactic equivalent of our modern-day shipping lanes. The emptiness provides a clear, hazard-free highway for future spacecraft traveling between the islands of galaxy clusters, potentially allowing for faster, safer travel without the need to navigate the complex and dangerous gravitational fields of dense matter. There's even the speculative possibility of resource extraction on a scale we can barely imagine. While matter is sparse, it is not absent. The diffuse hydrogen gas drifting through the void could, with technology millennia ahead of ours, be harvested and fused into heavier elements, providing a near-infinite supply of raw material. From a purely utilitarian perspective, the void is not empty. It is a treasure chest of space, energy, and potential. Yet, this utilitarian view clashes violently with a more preservationist ethic, one that argues for the intrinsic value of the void itself. This philosophy asks us to see these regions not for what they can do for us, but for what they are, the largest and most ancient natural features in existence. We have a tragic history on Earth of seeing a wilderness, a forest, a canyon, an ocean, and our first instinct being to develop it, to extract its resources, to bend it to our will, often with catastrophic and irreversible consequences for the native ecology. The cosmic void is the ultimate wilderness. It is a natural wonder that has evolved over billions of years through the fundamental forces of physics. To begin altering it, to fill it with our machinery and our infrastructure, would be an act of cosmic vandalism on an unimaginable scale. It would be like finding the last untouched rainforest on Earth and immediately deciding to pave it for a parking lot. Proponents of this view would argue that voids should be designated as the universe's first intergalactic wilderness parks, protected by international, or rather interspecies treaty, off limits to any form of development or resource extraction. Their value lies in their pristine state, as natural laboratories for pure science and as monuments to the awe-inspiring power and beauty of nature itself, serving as a humbling reminder of our small place in a vast cosmos. This debate is further complicated by the terrifying potential for unknown and unintended consequences. The void may seem inert, but it is a dynamic system governed by subtle gravitational equilibriums and permeated by dark matter and dark energy, forces we barely understand. Our activities on a scale large enough to be meaningful in a void could inadvertently disrupt these delicate balances. What if the concentrated energy collection or mass movement of a large-scale void operation somehow perturbed the local gravitational field, subtly altering the trajectories of galaxies on the void's boundaries over millions of years? What if our experiments or constructions somehow interacted with the dark energy fabric of space-time in a way that accelerated the void's expansion locally, with unforeseen repercussions for the larger cosmic web? We are like children contemplating rewiring the electrical grid of a continent. We simply lack the wisdom to predict all the possible outcomes of our actions in such a complex and poorly understood system. The precautionary principle, the idea that we should err on the side of caution when the risks are unknown and potentially catastrophic, would strongly argue for a hands-off approach until our understanding matures exponentially. Navigating this ethical minefield requires us to develop a completely new framework for cosmic law and interstellar environmentalism. We cannot apply the fractured, competitive, and often short-sighted models of geopolitics that have plagued Earth's history. The rules for the cosmos must be built on collaboration, foresight, and a deep reverence for the universe as a whole. This means establishing guiding principles now, long before we have the technology to act. Perhaps the most important principle is that of cosmic sustainability, the idea that any activity we undertake in space must be proven to have no net negative impact on the natural processes of the universe or the potential for other life to arise and flourish. It would mandate that the default position for pristine regions like voids is protection, and that the burden of proof for any development lies with those who wish to exploit, not with those who wish to preserve. This also forces us to confront profound questions about ownership. Can anyone or any nation truly claim ownership of a region of space that spans hundreds of millions of light years? Or do these great voids belong to all of humanity, or even to all potential sentient life as a common heritage? Answering these questions is the critical work that must begin today, in lecture halls and conference rooms, to ensure that when we finally do reach for the stars, we do so not as conquerors, but as thoughtful, responsible, and ethical stewards of the magnificent cosmos we are so fortunate to inhabit. Gazing into these immense cosmic voids, it's almost impossible not to feel a profound sense of personal insignificance. The sheer scale of it all can be utterly overwhelming. A single void can stretch for hundreds of millions of light years, a distance so vast that our entire human history, every triumph and tragedy, is less than a blink in the cosmic timeline. Our planet, our solar system, even our galaxy, become vanishingly small specks adrift in an ocean of near nothingness. This feeling, this cosmic vertigo, is a natural and deeply human reaction. It can be humbling, even intimidating, to confront the sheer immensity of a universe that seems so indifferent to our existence. Yet, if we sit with that feeling for a moment, a remarkable shift in perspective can occur. That initial sense of smallness doesn't have to lead to despair. Instead, it can be the gateway to a powerful sense of connection. We begin to see that we are not separate from this vastness, but an integral part of it. The very atoms that make up our bodies, the carbon in our cells, the iron in our blood, were forged in the hearts of long-dead stars that once shone in galaxies now lost within the cosmic web. We are not just observers of the universe, we are the universe become conscious, a way for the cosmos to look back upon itself and contemplate its own mysterious nature, emptiness and all. This realization transforms the void from a cold, alien emptiness into a fundamental part of our own extended being, connecting us to the grandest scales of existence in the most intimate way possible. This cosmic perspective is a powerful antidote to the myopia of our daily lives, where minor inconveniences can feel like world-ending catastrophes. The void offers a timeless vantage point, a reminder that our troubles, while real and important to us, are set against a backdrop of almost infinite space and time. It doesn't diminish our experiences, but rather frames them, granting us the resilience that comes from understanding our place in a larger story. It's the same resilience that allows a sailor to endure a storm by knowing the immense, steady presence of the ocean beneath them. The void is that ocean, and its silent, stable expanse reminds us that there is a fundament to reality that is constant and awe-inspiring, beyond the fleeting dramas of the moment. This perspective doesn't encourage apathy. On the contrary, it can fuel a more profound curiosity. If we are made of stardust and embedded in this magnificent cosmic structure, then our drive to understand it, to map the voids, to probe the dark energy accelerating their expansion isn't just an academic exercise. It is a form of self-discovery, a way for the universe to learn about its own anatomy through us. Our curiosity is the universe's curiosity. Our search for meaning is the universe seeking to understand its own purpose. On a more personal level, the science of voids offers a beautiful and unexpected metaphor for our inner lives. We all experience periods that feel like emotional or creative voids, stretches of emptiness, uncertainty, or stagnation where inspiration seems absent and direction is lost. Our instinct is often to fear this inner emptiness, to rush to fill it with noise, distraction, or busy work. We treat it as a problem to be solved, but the cosmos teaches us that emptiness is not a deficiency, it is a necessary space. Just as a cosmic void is not a true vacuum but a region of low density teeming with potential and governed by subtle forces, our own inner voids can be periods of immense potential. They are the negative space that gives form to our positive experiences, the quiet fallow periods that allow for new growth. In the silence and the stillness, stripped of the gravitational pull of constant activity, new ideas can percolate, new perspectives can form, and a deeper sense of self can emerge. The structure is still there, even when it isn't immediately visible. The beauty is in the underlying patterns waiting to be discovered. The potential for a new beginning is inherent in the quiet itself. Ultimately, the journey to understand the great cosmic nothings mirrors the most human of journeys, the embrace of the unknown. For millennia, we looked at the dark spaces between the stars and saw only absence, or perhaps projected our fears and myths onto them. It took courage, patience, and relentless curiosity to point our telescopes there and ask, "What is this really?" And what we found was far more wondrous than any simple myth, a dynamic, evolving architecture that holds the keys to the universe's past and future. This same principle applies to our own lives. When we confront the unknown within us or before us, a new challenge, a period of transition, a simple question we cannot answer, we have a choice. We can look away, fearing the emptiness, or we can lean in with the heart of an explorer, trusting that even in the deepest unknown, There is structure to be found, beauty to be uncovered, and profound potential waiting to be realized. The void, in all its terrifying and magnificent scale, is the ultimate teacher. It shows us that our smallness is our connection, that our curiosity is our compass, and that within every apparent emptiness, whether in the heavens or in our own hearts, lies not an end but a breathtaking new beginning. So as we reach the end of our journey into the heart of cosmic nothingness, it's staggering to reflect on the complete inversion of understanding we've just witnessed. We began by staring into what seemed like a simple, empty blackness, only to discover that these voids are not passive absences, but are, in fact, some of the most dynamic and influential architects of our entire reality. They are the negative space that gives the cosmic web its form, the expansive force accelerating the universe's fate, and the pristine laboratories where the most fundamental laws of physics are put to the ultimate test. This transformation in our comprehension from seeing nothing to appreciating a complex something is one of the most beautiful and humbling achievements of modern science. It proves that our universe is endlessly clever, hiding its deepest secrets not in the brilliant glare of starlight, but in the quiet, dark spaces in between, waiting for a curious mind to come along and ask the right questions. This revelation extends far beyond the equations of cosmology and into the very core of the human experience. These voids teach us a profound lesson about perception itself. They are a universal metaphor for the value of looking deeper, of questioning our initial assumptions. What we so easily dismiss as empty, barren, or insignificant often holds the most potential for discovery, whether we're gazing at the night sky or navigating the challenges in our own lives. The story of the void is a testament to the power of curiosity, a reminder that the drive to understand, to probe the unknown simply for the sake of knowing, is what elevates us. It's this insatiable wonder that has propelled us from ancient stargazers to a species that can map the invisible scaffolding of the cosmos. And it is this same spirit that will carry us forward into the next great era of exploration. And that next era is already dawning. The questions we've explored here are not closing chapters. They are the opening lines of a new and even more thrilling volume of discovery. The James Webb Space Telescope is peering back in time to find the very first galaxies being born in these underdense regions. The Vera Rubin Observatory will soon begin its monumental decade-long movie of the sky, tracking the subtle growth of voids in real time. The Euclid spacecraft and the Square Kilometre Array are preparing to map the dark matter within these emptinesses with precision we can scarcely imagine. Each new datum from these incredible machines will refine our models, challenge our theories, and undoubtedly present us with new, even more baffling mysteries we haven't even thought to ask yet. The journey to understand the void is accelerating faster than the voids themselves, and the greatest discoveries are undoubtedly still ahead of us. So the next time you find yourself under a clear, dark sky, I invite you to do more than just look at the stars. Take a moment to truly see the darkness that surrounds them. Let your eyes settle on that vast, deep black patch between the constellations. Now, knowing what you know, that simple act of observation becomes something entirely different. You are no longer looking at nothing. You are looking at the universe's largest structure. You are looking at a catalyst for galactic evolution. You are looking at a testing ground for dark energy and alternative gravity. You are looking at a potential gateway to other dimensions and a canvas for our deepest cultural fears and hopes. You are looking at the past, the present, and the ultimate future fate of all existence, all contained within that immense, beautiful, and dynamic nothing. That emptiness is now filled with meaning, and that is perhaps the greatest mystery